Before we begin on our journey to the mysterious moons of our solar system, let's take a look at what we call moons. Moons are celestial objects that orbit a planet like satellites. There are over 200 known moons in our solar system. To date, NASA has counted exactly 214. The Earth has only one moon. With the exception of Mercury and Venus, all the planets in our solar system have several moons. Even dwarf planets like Pluto and many of the asteroids in our solar system have moons. Let's take a look at the planets in our solar system. Our neighbor Mars has two moons, Phobos and Deimos. These two moons are small bodies orbiting a few thousand kilometers from the red planet. Subject to the tidal forces of Mars, they rotate synchronously, meaning they always face the same direction as the planet. Their orbits evolve over time. Phobos moves closer to Mars, while Deimos moves further away. Let's continue moving through the solar system away from Earth. Neighboring Mars, the gas giant Jupiter is the planet with the most moons, with 92 confirmed satellites. Io, Europa, Ganymede, and Callisto, Jupiter's four largest satellites, are called Galilean satellites as they were discovered by Galileo in 1610. In fact, they were the first moons to be discovered after our own. Saturn is the second planet with the most moons, with 144 confirmed satellites, of which 66 have been given official numbers and 63 their own names. Saturn's two best-known moons are Enceladus and Titan, which we'll explore later in this trip. After Saturn comes the planet Uranus. 4 times larger than the Earth, it is the third largest planet in the solar system after Saturn. Along with Neptune, it is one of the 2 icy planets in our solar system. Uranus has 27 moons. The first 2 satellites of Uranus to be discovered, in 1787, Titania and Oberon, take their names from Shakespeare's play. Titania is the largest satellite of Uranus and the 8th largest in the solar system. Neptune has 14 confirmed satellites, the largest and first to be discovered in 1846 being Triton. Pluto, demoted to dwarf planet status in 2006, is part of a double system with Charon, one of its satellites. Pluto's 4 other satellites are Styx, Nix, Kerberos, and Hydra. Let's turn first to Jupiter, the largest planet in our solar system, but also the one with the most moons. Jupiter is the 5th planet in the solar system in order of distance from the Sun, from which it is 779 million kilometers, or 485 million miles on average. This gas giant is the largest planet in size and mass, ahead of its neighbor Saturn. Its average radius is 69,911 kilometers, or 43,500 miles, or 11 times that of the Earth, and its mass is 318 times that of our planet. In fact, Jupiter is so huge that it has been visible to the naked eye since prehistoric times. After the Sun, Moon, and Venus, Jupiter is the 4th brightest object in our night sky. In fact, Its great luminosity is the origin of its name, which comes from the Roman god Jupiter, master of the other gods. Composed mainly of hydrogen and helium, Jupiter's composition is similar to that of the Sun. Although it has a rocky core of heavy elements, it has no solid surface. In its atmosphere, several elements have been detected, including methane, ammonia, sulfur and nitrogen compounds, and water ice. Jupiter, its 92 moons and rings, are known as the Jovian system. But the giant planet's influence extends far beyond the Jovian system. This influence is exerted, for example, on Jupiter's Trojan asteroids, a group of asteroids that share its orbit around the Sun. The first space probe to fly over Jupiter was the American Pioneer 10 in 1973. Until 1979, the planet was explored by Pioneer and Voyager 1 probes. Then between 1995 and 2003, the Galileo probe orbited Jupiter, followed by the Juno orbiter in 2016. Juno is currently still orbiting Jupiter, until at least 2025. Unfortunately, we've long known that the chances of Jupiter harboring life are remote. Not only does Jupiter have no solid surface, but its presence and internal temperatures are extreme. No biological object could survive on this type of planet. So why do Jupiter exploration programs continue to fuel the hopes of alien hunters? Because Jupiter has 92 moons, 4 of which could potentially be habitable. These are the famous Galilean moons. That Jupiter's moons are habitable is hardly surprising. The Jovian system is often compared to a miniature version of the solar system. Jupiter accumulated so much thermal energy due to gravitational contraction during its formation that it now releases more thermal energy than it receives from the Sun. It could therefore act for its moons like the Sun for the planets in our solar system. Jupiter's 4 Galilean moons were discovered by Galileo in 1610. The Italian astronomer gave his name to these satellites, although they may have been observed earlier by the Chinese astronomer Gan Day in 362 BC. Between the end of the 19th century and the early 1650s, 8 other satellites of Jupiter were discovered: Amalthea, Himalaya, Elara, Pasiphae, Sinope, Lysithea, Carme, and Anakie. Leda and Themisto were discovered in the 1970s. So, before the arrival of space probes on Jupiter, 14 satellites of the Jovian system were already known. In 1979, 3 more moons were discovered. The number of known satellites was increased to 63 by new observations at the turn of the century, and from 2010 onwards, new observations expanded the catalog of Jovian moons. The last 15 known satellites were discovered very recently, in 2022 and 2023. So it's possible that more will be found in the years to come. It's true that at first glance, Jupiter's moons don't seem very hospitable. They are far from the Sun, almost all encased in ice, and their atmosphere is very sparse. But their observation has revealed some fascinating facts that are well worth investigating. Galilean moons are likely to conceal liquid oceans beneath their icy crusts. And liquid water means the development of biological organisms. What's more, the thick ice crust could provide good protection against radiation and meteorites, as well as thermal insulation conducive to the development of life, a bit like our atmosphere on Earth. But let's take a closer look at these moons to find out more about their potential for harboring life. Fasten your seatbelts as we explore Jupiter's 4 Galilean moons: Io, Europa, Ganymede and Callisto. Let's start with Io, perhaps the moon in the Jovian system least likely to harbor extraterrestrial life. You'll soon see why. Io is also called Jupiter 1, perhaps because it is the satellite of Jupiter whose orbit is closest to the gas giant. Its period of revolution is just 42 hours. It is Jupiter's third largest moon and the fourth largest in the solar system. But it's also the densest and most geologically active, with over 400 active volcanoes. The fact that Io is so volcanically active first surprised scientists. When the Voyager probe flew over Io, it detected something unexpected on its surface: hundreds of giant active volcanoes. Other probes have since spotted huge lakes of molten lava. These discoveries are quite astonishing, as volcanic activity on Earth is fueled by the heat of the Earth's core. However, Io is so small that it must have cooled down completely billions of years ago. The only possible explanation was that Io certainly conceals in its core another source of energy that can continuously fuel this volcanic activity. The observation of volcanoes on Earth and the data collected on Io enabled us to imagine what life would be like on this moon. Living on Io would mean living in an extremely hostile environment, very cold or very hot, with no atmosphere. If you were to walk on Io, you would bounce slightly because the gravity on Io is the same as on the moon, 6 times less than on Earth. You could walk through black lava fields and witness phenomenal volcanic eruptions. Because on Io, eruptions are extremely spectacular. The gases released by the lava project clouds into the interstellar void. On its way to Pluto, NASA's New Horizons probe passed close to Jupiter in March 2007 and photographed an impressive volcanic eruption on Io. The eruption was that of the Tvashter volcano. The images taken at the time by the probe's high-resolution telescopic camera are impressive. They show a plume over 300 kilometers, or 185 miles high, rising in Io's northern hemisphere, and then raining down on the surface. These images provide researchers with proof that volcanic eruptions on Io are violent and powerful. But what could be generating so much energy in the heart of this frozen moon? In fact, this intense geological activity is the result of tidal heating. This heating is due to the friction generated inside the moon by its gravitational interactions with Jupiter and 2 other Galilean satellites, Europa and Ganymede, with which it is in orbital resonance. In other words, with each of its revolutions in its elliptical orbit around Jupiter, Io is buffeted by the gas giant's gravitational forces. When it reaches the point in its orbit closest to Jupiter, it undergoes a deformation of over 100 meters or 330 feet. Imagine this over billions of years, and you can see how intense friction could have arisen within this small moon. It's a bit like twisting and unfolding a piece of metal. It will eventually heat up. It's the same for Io. These movements and deformations have created an alternative energy source at the heart of Io, capable, in theory, of promoting life. Remember, life needs 3 elements to emerge, including a source of energy. With these discoveries, researchers realized that they had to stop believing that habitable celestial objects had to resemble the Earth in every way, and that habitable zones were necessarily dependent on the Sun. The perimeter likely to harbor life extended from the Earth to the farthest reaches of the solar system. However, the probability of life existing on Io remains very low. Yes, Io has an energy source. Yes, Io could contain the chemical elements that make up life, which would have been disseminated like on Earth by comets and asteroids billions of years ago. But researchers have never succeeded in finding the third element necessary for the emergence of life: liquid water or its equivalent. Why couldn't there be liquid water under Io's volcanic crust? Because, unlike other moons, Io is not made of water ice, but of silicate rock, surrounding a molten iron or pyrite core. Although the chances of Io harboring any form of life are slim to none, researchers are nonetheless interested in this moon for its intense volcanic activity. The interest of these volcanoes is not only scientific, but also aesthetic, as the images of this moon are magnificent. Io's volcanoes produce plumes of sulfur and sulfur dioxide, which, after rising several hundred meters, rain down and cover the moon's vast plains with a frosty layer of material. This material also forms a thin layer of atmosphere. Lava flows can extend over 500 kilometers or 310 miles in length. The moon's surface is constantly changing, taking on shades of yellow, red, green, white, and black. Io's surface is also dotted with over 100 mountains, the result of tectonic phenomena on the moon's silicate crust. Some of these mountains rise very high, even higher than Mount Everest, even though Io's radius is 3.5 times smaller than Earth's. Impressive, isn't it? There's no doubt that researchers won't be giving up their observations of this moon, which still conceals so many mysteries other than that of life. Let's continue our exploration of the Galilean moons with Europa, or Jupiter 2, the 6th closest moon to Jupiter. Europa has a period of revolution of 85 hours. With a diameter of 3,122 kilometers, or 1,900 miles, it's the smallest of the Galilean moons, but the 6th largest in our solar system. It's also the most interesting in the search for extraterrestrial life. In fact, according to researchers, it's the one where life is most likely to be found. Let's take a closer look at this mysterious moon. Europa has been flown over 12 times by NASA's unmanned spacecraft Galileo. Virtually all our data on Europa was collected by this probe. Europa is barely smaller than our moon. It consists mainly of silicate rock, with a crust of water ice and a core, probably of iron and nickel. It has a very thin atmosphere composed mainly of oxygen. Its temperature at the equator is minus 183 degrees Celsius or minus 297 degrees Fahrenheit. And its temperature at the poles can drop to minus 223 degrees Celsius or minus 370 degrees Fahrenheit. Unlike Io or our moon, its surface is free of craters, making Europa the smoothest surface celestial object in the solar system. Its surface is relatively young, estimated to be just 100 million years old. Locked in by Jupiter's tides, Europa rotates synchronously around the gas giant, so it always presents the same face. Small deviations in its rotation have been observed. All these observations could mean that there is a liquid layer between the surprisingly smooth surface of this small moon and its rocky core. This hypothesis was confirmed by the Galileo probe studies of the satellite's interaction with Jupiter's magnetic field. While there are no impact craters on Europa's surface, there are glacial striations and fissures known as lineae. These crevices have been analyzed by the Galileo probe. The analyses show that in the past, the satellite's crust moved 80 degrees in relation to its interior, which would have been impossible without a liquid layer beneath the surface. What's more, as the Galileo probe got closer to Europa, it was able to observe these cracks more closely. The data collected suggests that in some places the ice cracked, then a trench formed, and a material filled the empty cracks and froze, allowing the parts to be welded back together. It's a bit like kintsugi. The probe also showed huge fields of jagged ice, as if the ice had melted and then roughly reconstituted itself, reminiscent of the ice that covers our oceans on Earth. The Galileo probe also took measurements of Europa's magnetic field. Analyses revealed the presence of an electric current that could correspond to that of a salty ocean of liquid water. According to the prevailing model, Europa's slightly eccentric orbit, maintained by its orbital resonance with Io and Ganymede, causes a tidal heating effect, allowing the ocean to remain liquid. This leads to a movement of ice, similar to plate tectonics, the first time this mechanism has been found anywhere other than on Earth. Like Io, Europa is therefore heated by internal friction due to its interaction with the gravitational fields of Jupiter and the satellites with which it is in orbital resonance. This may explain the jagged ice, which appears to have been melted and then refrozen. These interactions would cause powerful tidal waves in its inner ocean, further raising the temperatures inside the satellite. All this makes the presence of a liquid ocean possible. According to the researchers, this internal ocean could be as deep as 100 kilometers or 60 miles, with a volume twice that of our oceans on Earth, nicknamed the Blue Planet. Europa thus appears very different from its sister moon Io. It is covered by an exceptionally smooth and clean layer of ice. The highest features of its relief rise only a few hundred meters above the surface, a completely different landscape from Io's high mountains. The thickness of the ice crust varies between 10 and 30 kilometers or 20 miles. Europa's surface is striated by a network of long, deep fissures. Some of these cracks may be reaching the groundwater layer. If this is the case, the ice that covers the bottom of the crevices provides valuable material for studying Europa's interior composition. Europa's geysers occur regularly throughout the Moon's orbit, but are most frequent when the Moon is furthest from Jupiter. This is because Jupiter's tidal forces are weaker when the Moon is further away. These tidal forces are responsible for the formation of geysers, forcing water from the underground ocean towards the surface. These geysers, detected by the Hubble telescope, can reach up to 200 kilometers or 125 miles in height. These giant jets are made up of water vapor, a surprisingly clean form of water. It's possible that this water comes from Europa's underground ocean, or from giant lakes hidden beneath the ice crust. These are invaluable to scientists, as they would enable them to detect traces of life without having to use a lander. For the moment, nothing is certain. In the absence of concrete data, the composition of Europa's ice crust is currently estimated on the basis of one of its largest craters. Spectral analysis of the craters reveals compounds of magnesium, sulfur, iron, and hydrogen peroxide. Conclusion: there is certainly a wide diversity of minerals in the satellite's hidden hydrosphere. It's also important to point out that Europa's atmosphere contains oxygen, which is formed when icy water is broken down by UV rays. But Europa's gaseous envelope remains a trillion times sparser than that of the Earth. In any case, according to some calculations, the oxygen concentration in Europa's oceans could be sufficient to sustain single-cell aerobic life. Aerobicity is the ability of an organism or microorganism to thrive in ambient air using oxygen. Europa has liquid water and the building blocks of life. We still need a third element to affirm that life can develop there, a source of energy. And it does have a source of energy, undersea volcanoes that saturate the water with sulfur and iron oxides. Some researchers even claim that there could be multicellular organisms in the European Ocean, but this hypothesis is still premature. In any case, all we know is that we can't rule out the possibility of primitive life on this mysterious moon of Jupiter. Faced with all these possibilities, researchers are wondering whether it is really possible for a form of life to survive in this type of environment, namely, a cold liquid ocean enclosed beneath kilometers of ice, with no access to the sun's energy, and with underwater volcanic activity as its sole source of power. The answer could lie on Earth. Biologist Tim Schenck has explored the waters of our planet that bear the closest resemblance to the icy depths of the Jovian satellite. 320 kilometers or 200 miles from the North Pole, the biologist sent robots 3,600 meters or 12,000 feet deep beneath the Arctic ice sheet, where sunlight never breaks through. In other words, the robots were sent into an ultra-hostile environment where temperature and pressure levels are extreme due to underwater volcanic activity. The aim? To understand what might be going on beneath Europa's ocean by observing the most hostile underwater environments on our planet. At depths of 3,600 meters or 12,000 feet in the heart of the Arctic Ocean, Tim Schenck's robots, unsurprisingly, collected evidence of a very hostile environment. volcanic fissures spew water at 370 degrees Celsius or 698 degrees Fahrenheit, saturated with toxic chemical compounds such as hydrogen sulfide. This type of fissure is more than likely to be found in the depths of Europa's oceans. Surprising as it may seem, Tim Schenck has discovered living organisms around these cracks. These cracks are in fact lined with microbes for miles around, new forms of life that we never knew existed, but which are indeed living organisms. Even the polar oceans on Earth harbor microbial life, so why not on Europa? How do these microbes survive in such a hostile environment? Instead of using the sun's energy, they use sulfur, methane, and hydrogen as a source of chemical energy. The next step is to land a probe on Europa to verify the scientists' theories. But for that, we'll have to wait a little longer. For one thing, the moon is 628 million kilometers away. What's more, we'd have to build a robot capable of crossing kilometers of ice, then swimming in the icy water to collect data. This is already a complex task on Earth, so imagine it over 600 million kilometers from our planet. Are moons that generate heat as they make their revolution, causing the ice to melt and underground oceans to form, ideal for the development of life? A far-fetched idea? Perhaps not, as Europa is not the only moon that could fit this model. Ganymede, or Jupiter 3, is the third Galilean satellite. Its orbit lasts about 7 Earth days. It is not only Jupiter's largest satellite, but also the largest in the entire solar system. In fact, it's the satellite that most closely resembles a planet. Its diameter is 5,268 kilometers, or 3,000 miles, or 8% larger than the planet Mercury, and 2% larger than Saturn's largest moon, Titan, which we'll study later. However, its mass is only 45% that of Mercury, as it is made up of equal amounts of water ice and silicate rocks, whereas Mercury is made up solely of rocks and metals. Ganymede is just over twice the size of our moon and twice as heavy as our satellite. You can see it with the naked eye in our night sky. It's the only satellite in our solar system with a liquid metal core and its own magnetosphere. This magnetosphere was probably created by convection within the liquid iron core. Ganymede completes its orbit around Jupiter in 7 Earth days, around 1 million kilometers from the gas giant. Its orbit is slightly eccentric and inclined to Jupiter's equatorial plane. Its rotation is controlled by Jupiter's gravitational tidal effects, like Io and Europa, so it too is in synchronous rotation. When Ganymede makes one complete revolution around Jupiter, Europa makes 2 and Io 4. Ganymede is therefore in orbital resonance with the other 2 Galilean moons. Ganymede's atmosphere is thin and contains several elements: atomic oxygen, dioxygen, and possibly ozone, as well as atomic hydrogen in small proportions. Pioneer 10 was the first probe to take a close look at Ganymede. In the 1970s, the American probes Pioneer 10, Pioneer 11, and Voyager 1 and 2 provided some insight into Ganymede. Then, the Galileo probe refined some of the data we have on this Jovian satellite, thanks to 6 close flybys between 1996 and 2000. Thanks to Galileo's data, we were able to discover its underground ocean and magnetic field. Like Europa, Ganymede is thought to have an ocean under its surface ice, which could contain more water than all the oceans on our planet put together. 1/3 of the satellite's surface is covered by 4-billion-year-old impact craters, and 2/3 by lighter-colored regions cut by wide grooves. This relief is probably the result of tectonic activity, triggered by tidal heating, although for the moment it remains a mystery to scientists. Some researchers believe that Ganymede has an ocean sandwiched between 2 layers of ice, while others think that there are several layers of ocean separated by different layers of ice, a bit like a mill fuel of water and ice. Ganymede's magnetic field is due to its iron-rich liquid core. As the magnetosphere is essential to protect us from radiation coming from space, the existence of this magnetic field is an argument in favor of the presence of life on this moon. Ganymede's magnetic field produces polar auroras, as shown by images taken by the Hubble Telescope in 1995. Another feature of this magnetic field is that it is contained within the larger magnetic field of Jupiter. Studies of Ganymede's magnetic field by the Galileo probe show that there could be a multi-layered salty ocean beneath the ice crust at a depth of at least 200 kilometers or 125 miles. Multi-layered because this ocean could have up to 4 layers, each with its own salinity and density. These 4 layers would be separated by ice. On the surface of Ganymede, Galileo's high-resolution spectroscope has revealed the presence of a large number of non-aqueous materials. These include carbon dioxide, sulfur dioxide, sulfuric acid, various organic compounds, magnesium sulfate, and sodium sulfate. These materials probably originate from Ganymede's subglacial ocean, although it is not yet known by what mechanisms these compounds could have reached the surface by penetrating the satellite's crust. Researchers believe that Ganymede may have formed by accretion, i.e., the progressive agglomeration of the gases and dust that surrounded Jupiter after its formation. The average surface temperature of Ganymede is -148 degrees Celsius or -234 degrees Fahrenheit. A decay process inside Ganymede would heat the satellite even more, so that the core would have an average temperature of 1200 to 1400 degrees Celsius or 2550 degrees Fahrenheit. The presence of oxygen in Ganymede's atmosphere is not in itself proof of the presence of life on this satellite, as molecular oxygen can result from the decomposition of water ice under UV light. During this process, hydrogen evaporates into space, and oxygen, a heavier element, is deposited on the surface. For the moment, nothing is certain, but Ganymede remains a moon to keep a close eye on in the quest for extraterrestrial life in our solar system. We're now going to explore Jupiter's last Galilean moon, Callisto. Callisto, or Jupiter 4, is the second largest Jovian moon after Ganymede and the third largest in the solar system. It is the Galilean moon furthest from Jupiter, and therefore the only one of the 4 not to be in orbital resonance. Like Ganymede, Callisto is thought to have formed by accretion from the disk of gas that surrounded Jupiter after its formation. With a diameter of 4,820 kilometers or 3,100 miles, Callisto is roughly the size of Mercury. This moon has a thick crust of ice, 80 to 150 kilometers deep. It is made up of roughly equal parts rock and ice. However, it has one major difference from Ganymede. It does not undergo tidal heating and is therefore only partially differentiated. In other words, it does contain layers at different densities, but not at full depth. According to data collected by the Galileo probe, Callisto may have a small silicate core and an ocean of liquid water more than 100 kilometers beneath its surface. As on Ganymede and Europa, this ocean could harbor life. Its depth is estimated at between 50 and 300 kilometers, depending on the model, and its temperature would be around minus 20 degrees Celsius or minus 4 degrees Fahrenheit. Because of the high pressure, the water in this ocean would remain liquid. But beneath this ocean probably lies a layer of ice 300 kilometers or 185 miles thick, and a core composed of ice and rock. Callisto's surface is old, heavily cratered, and shows no sign of tectonic activity. Because Callisto is further from Jupiter than the other Galilean moons, its surface is less affected by the gas giant's magnetosphere. Callisto is surrounded by a thin atmosphere composed mainly of carbon dioxide and probably molecular oxygen, as well as by an intense ionosphere. Explored on numerous occasions by space probes such as Pioneer 10 and 11, Galileo, and Cassini-Huygens, Callisto is often considered the most suitable body for a human base to explore the Jovian system. However, the likelihood of this satellite harboring any form of life is lower than for Europa or Ganymede. The impact of Jupiter's tides is not enough to properly deform the satellite, as Callisto is located too far from Jupiter. As a result, the satellite cannot draw much heat from the gas giant. What's more, Callisto is made up mainly of ice, whereas it would be preferable for water to be in contact with hard rock to be saturated with the elements necessary for the appearance of life. In fact, the low diversity of chemical compounds and low temperatures on this satellite considerably reduce the chances of life appearing and developing. But this possibility should not yet be totally ruled out. Unfortunately, no more is currently known about the possibility of extraterrestrial life on Jupiter's moons. These moons have been explored only briefly, by spacecraft en route to another destination. But more recently, projects dedicated to the study of Jupiter and its moons have emerged. NASA's Juno probe arrived in Jupiter's orbit in July 2016, and has since delivered extraordinary images of the gas giant. In July 2021, it moved on to study the Galilean moons. On September 29, 2022, it flew very close over the moon Europa, passing just 352 kilometers or 220 miles from its surface. This was only the third time a probe had flown over this satellite. The flyby enabled the probe to take photos of the moon, as well as samples, to be compared with Galileo data collected at the beginning of the century. On October 16, 2023, images of Io were revealed by the American probe, which passed within 11,000 645 kilometers, or 7,500 miles of the Moon. The European Space Agency's JUICE project is also eagerly awaited. Its aim is to study Jupiter and the 3 Galilean moons that could harbor life: Ganymede, Europa, and Callisto. JUICE stands for Jupiter Icy Moons Explorer. The probe was launched on April 14, 2023, and is scheduled to arrive in orbit around Jupiter in 2031, after a 7.5-year journey. This positioning will enable it to fly repeatedly over the Galilean moons to collect data. Researchers have high hopes for this project, because if all goes well, it could considerably enrich our knowledge of Jupiter and its satellites. In December 2034, the probe will orbit Ganymede to study this satellite in greater depth, before completing its mission in September 2035. Another mission is being developed by NASA, this time to study the moon Europa in depth. This is Europa Clipper. This automatic probe should leave Earth in October 2024 and reach the Jovian system in April 2030. These projects are promising and should help us learn more about the presence or otherwise of highly resistant living organisms in the subterranean oceans of these moons. Researchers don't expect to find little green men on these satellites, but rather simple organisms like those found on Earth, at the bottom of the oceans near areas of volcanic activity. But it's a good start, since life on Earth probably evolved from these ultra-resistant microorganisms. Could there be other moons in our solar system with conditions similar to Europa, Ganymede, or Callisto, suitable for the appearance and development of life? The Cassini-Huygens space mission was designed to answer this question. Its objective? To explore the Saturnian system, i.e., the planet Saturn and its satellites, determine how Saturn's rings were formed, and inspect some of the giant planet's moons. This mission, developed by NASA with the participation of the European Space Agency and the Italian Space Agency, was launched on October 15, 1997, and ended on September 15, 2017. After flying past Jupiter on December 30, 2000, the probe was placed in orbit around Saturn on July 1, 2004. On January 14, 2005, the Huygens lander detached from the probe and landed on the surface of Titan, Saturn's largest moon, while the Cassini orbiter continued to collect data on Saturn and its satellites as they passed close to the gas giant's orbit. The mission was scheduled to last 4 years but was extended twice, ending on September 15, 2017. The Cassini orbiter was equipped with the most sophisticated instruments ever taken to the outer solar system: cameras, spectrometers. Particularly costly, this mission was a real success, as it provided scientists with a wealth of data on the Saturnian system, Saturn, its magnetosphere, its rings, Titan, and the other satellites of this giant planet. Thanks to the Cassini-Huygens space mission, Saturn's rings have been revealed in detail for the first time. These rings stretch for thousands of kilometers, yet in some places they are no thicker than a few dozen meters. The Cassini probe has confirmed that these rings are made up of billions of shiny particles of almost pure water ice. These particles vary enormously in size, from a speck of dust to a mountain. The data collected has also made it possible to date the rings. They were created less than 100 million years ago and should disappear in less than 100 million years. But above all, the Cassini-Huygens mission has also enabled us to refine our knowledge of Titan and to discover astonishing features of Saturn's other moons, notably Enceladus and its geysers, clues to an underground ocean that could perhaps harbor a form of life. In all, Saturn has 146 satellites, 144 of them confirmed. It also has more than 150 helices in its rings, which could be minor moons, i.e., particularly small natural satellites. At least 150 minor moons have been detected in Saturn's rings through the disturbances they create in their environment. But researchers suspect that this is only a small portion of the total population of these objects. Saturn's satellites vary in size, from less than a kilometer in diameter to 5,149 kilometers or 3,200 miles in diameter for its largest satellite, Titan, which is larger than the planet Mercury. We'll now take a look at Saturn's two most notable satellites, Titan and Enceladus. Let's begin our journey into the heart of the Saturnian system by exploring Titan, the largest of Saturn's moons. Titan, or Saturn VI, is the second largest moon in the solar system after Ganymede. It was the first moon of Saturn to be discovered by Dutch astronomer Christian Huygens in 1655. One of Titan's special features is that it is the only known satellite to have a dense atmosphere. Its atmosphere is made up of 98.4% dinitrogen and 1.6% methane and ethane, and lies between 200 and 880 kilometers in altitude, i.e., almost 500 miles above sea level. To give you a point of comparison, on Earth, 99.99% of the mass of the atmosphere is less than 100 kilometers or 60 miles above sea level. It's also difficult to obtain a spectrum of Titan's surface, as its atmosphere is opaque over a wide range of wavelengths. Titan's atmosphere contains layers of opaque fog that block out most of the sun's light, so much so that the Huygens probe team described the process of photographing Titan's surface as photographing an asphalt-covered parking lot at dusk. The temperature of the atmosphere is around minus 180 degrees Celsius, or minus 292 degrees Fahrenheit, and reaches minus 200 degrees Celsius, or minus 328 degrees Fahrenheit, at the tropopause, at an altitude of 40 kilometers, or 25 miles. According to observations by the Voyager probes, the pressure at the satellite's surface exceeds 1.5 times that of the Earth. Titan is composed mainly of rock and frozen water. Its surface is geologically young, with a few mountains and cryovolcanoes, but overall, a relatively flat and smooth surface, with few impact craters. Winds and methane rains, which are frequent on Titan, create dunes and coastlines on the satellite's surface, just like on Earth. Titan also has seasons. When Cassini's Huygens module visited Titan in 2004, it detected elements of life in its atmosphere. But that's not all. As it flew over the moon, it detected something mysterious, partly hidden by the clouds gathering over its south pole, resembling a lake of water. Numerous flybys subsequently revealed the existence of hundreds of such lakes, scattered across the moon's north and south poles. What is the significance of these mysterious lakes? Could it be that, as on Earth, they are lakes of water with a rich ecosystem? This question has intrigued researchers, as Titan is the only known environment other than Earth to feature liquid expanses on its surface. But given Titan's surface temperature of minus 180 degrees Celsius or minus 290 degrees Fahrenheit on average, these lakes cannot be lakes of liquid water. After analyzing the infrared waves reflected by the lakes, the researchers concluded that they were in fact liquid methane and ethane at very low temperatures. On Earth, these elements are used as fuel in gaseous form. But on Titan, liquid methane digs valleys, forms clouds, and falls as rain. In fact, it behaves exactly like water on Earth. Researchers then wondered whether this methane could be conducive to the formation of life, allowing organic molecules to dissolve, mix, and interact, just like water on Earth. Our theory of life includes the need for a liquid element. On Earth, water enables organic molecules, the basic ingredients of life, to dissolve, assemble, and interact with each other to form larger, more complex molecules, destined to develop into living beings. But could another liquid do the trick? Could the building blocks of life dissolve in methane and give rise to life? Astrobiologist Chris McKay has attempted to answer this question. To do so, he used the elements detected in Titan's atmosphere by the Cassini mission and carried out a simulation. First, he reproduced the reaction that takes place on Titan to obtain the same organic material as in its atmosphere. Next, he recreated the lakes detected by the Huygens module's radars by filling a test tube with methane gas, which he cooled to minus 143 degrees Celsius or minus 225 degrees Fahrenheit using liquid nitrogen. The methane liquefied exactly as it does on Titan's icy surface. Chris McKay was thus able to obtain a miniature Titan lake in his test tube, namely, a bath of liquid methane with organic materials. The aim now is to find out whether these materials will dissolve to form more complex molecules and ultimately a new form of life. If these organic materials can dissolve, it means that the chemical processes necessary for life could exist on Titan, and on a larger scale, that they are capable of being triggered even in conditions of extreme cold and in liquids other than water. This would also mean that life has arisen twice under different conditions, and that it is therefore a natural process that can appear in other places. This would open up infinite possibilities. In any case, if there is life on Titan, it bears no resemblance to life on Earth. While we await the results of Chris McKay's experiment, other evidence of possible life on Saturn's satellite has been put forward. A team of researchers has identified a deficit of acetylene on Titan's surface. This molecule, which forms on the planet's surface, should be present in Titan's lakes, but has not yet been detected. According to Chris McKay, Acetylene could indeed be the food of choice for hypothetical life based on liquid methane, but nothing is certain yet. The lack of acetylene could just as easily result from the action of sunlight or cosmic rays, which are capable of transforming acetylene into other, more complex molecules that no longer display its spectral signature. Whatever the case, researchers are still hopeful of finding some form of life on Titan. This moon of Saturn closely resembles a primitive Earth, albeit at a lower temperature in many respects. Its liquids on and below the surface, its thick atmosphere of diazote, Titan could well contain extraterrestrial microbial life, or at least a prebiotic natural environment rich in complex organic chemistry. Another of Saturn's moons has attracted the curiosity of researchers, Enceladus. On the face of it, this satellite isn't the most interesting. It's only Saturn's 6th in size and 14th in distance. But since the Voyager 2 and Cassini-Huygens missions, researchers have been taking a close interest in this small moon, which boasts some astonishing features. Enceladus is a real mystery, very different from Saturn's other moons in its appearance and shimmering white surface. It displays a complex geological activity, difficult to explain for such a small body. Indeed, Enceladus measures only 500 kilometers or 310 miles in diameter on average. However, the Cassini probe has spotted cracks, protrusions, and fissures on its surface, showing that there has indeed been activity on this moon. In fact, one of the objectives of the Cassini-Huygens mission was to find out whether this geological activity was still taking place today. Take a close look at these images taken by the Cassini probe. You can see 4 strange blue faults running parallel down towards the South Pole. These faults have been nicknamed the Tiger Stripes. 120 kilometers, or 75 miles long, they are several hundred meters deep and bear disturbing similarities to earthly faults. The probe's thermal sensors recorded some surprising data at Enceladus's South Pole. While these faults should be colder than the rest of the moon, they radiate heat. In fact, the faults are on average 95 degrees Celsius or 200 degrees Fahrenheit hotter than the rest of the moon. The mystery surrounding Enceladus thickened when the probe changed its perspective. As Enceladus passes in front of the Sun, immense geysers can be seen, erupting from the Tiger Stripes. These immense jets of matter rise up to hundreds of kilometers. So, does Enceladus harbor an energy source like Io or Europa that could explain these geysers? The answer is yes. Like the 2 Galilean moons, friction generated by gravitational forces causes the moon to heat up and melt ice. As it approaches Saturn, the moon Enceladus undergoes a torsion that creates internal heating, exactly what happens when a piece of metal is bent. The jets observed by the Cassini probe are in fact liquid water vaporized in space, freezing on contact with its icy temperature. These jets are propelled at an impressive speed of nearly 200 kilometers per hour or 125 miles per hour. So there could be liquid water beneath the surface of Enceladus. The Cassini-Huygens space mission team programmed the probe to pass through these jets in order to sample particles and better understand their origin. After several passes, the probe detected some of the elements that make up living organisms. The discovery confirmed that yes, there could be life on Enceladus. The moon contains 3 elements needed to be considered potentially habitable: liquid water, a powerful heat source, and organic material. What would life be like on Enceladus? Around the tiger stripes, we'd be in a region of eternal snow, since it's been snowing on Enceladus for at least 100 million years. The sky would be black, and we'd have the impression of floating due to the low gravity. We wouldn't be able to see anything with the sun at our backs, but facing the sun, we'd be able to see the immense geysers cut through the light and fall to the ground in a thick white mantle. For the moment, there is no evidence that Enceladus harbors life. Cassini's instruments have not detected any trace of life as such. But Enceladus is definitely on the list of next destinations to visit during space exploration missions. What's more, to analyze the moon's underground water content, you don't have to dig as you do on Europa. Just walk through the geysers. All the particles are sent into space, ready to be collected and analyzed. Apart from the Saturnian and Jovian systems, are there any other moons in our solar system that could potentially be habitable? Of the 214 moons identified by NASA, there must be more. To answer this question, scientists have turned to Uranus, Neptune, and Mars. Uranus and Neptune were overflown in the 1980s by the Voyager 2 probe. Scientists held out little hope of the habitability of these icy planets, which could not harbor liquid water, but after the discovery of oceans in unlikely places, the data collected on these planets and their satellites was revised. Uranus has 27 moons, but only 5 have been analyzed in depth: Titania, Oberon, Umbriel, Ariel, and Miranda. If an internal ocean existed on Miranda, the smallest of the satellites studied, it would probably have frozen over by now. But it's entirely possible that the other 4 moons contain an internal ocean. Depending on the moon, scientists have developed different scenarios to explain the origin of an energy source. On Titania and Oberon, the 2 largest satellites, heating is thought to be due to the tidal effect of Uranus, while on Ariel, it could be explained by cryovolcanic activity. The scientists' conclusion is that there may be internal oceans on the Uranian satellites, but they are relics of former oceans, or residual oceans, rather than thick oceans. And what about Neptune? The 8th planet from the Sun, Neptune, like Uranus, is what we call an icy planet. Of its 14 satellites, the one that most interests researchers is Triton, its largest, with a diameter of just over 2,700 kilometers, or 1,700 miles. Triton is an astonishing moon. It's the only known large satellite in the solar system to orbit in the retrograde direction, i.e., in the opposite direction to the planet's direction of rotation. For this reason, Triton may be a Kuiper Belt object captured by Neptune. It is also the only moon, along with Phobos, one of Mars' 2 moons, to approach the object around which it orbits. Our moon, on the other hand, is moving away from the Earth by about 3.8 centimeters, or 1.5 inches per year. While flying over Triton, Voyager 2 observed geysers 8 kilometers or 5 miles high over 180 kilometers or 60 miles, all concentrated in the region of Triton, currently facing the Sun. These geysers would therefore have a solar origin. Researchers believe that Triton harbors fairly recent cryovolcanic activity, which explains the nature of the terrain observed by the Voyager 2 probe on its surface. Like Europa, Ganymede, Titan, and Enceladus, Triton could be home to an underground liquid ocean. To find out more, a mission project had been developed, the Trident mission, but it was not selected to be part of NASA's Discovery program. Instead, missions to Venus were chosen. No doubt another mission will be developed to answer the many questions scientists have about this mysterious moon. Where do its geysers come from? Why is its landscape constantly changing? Why does it have an intense ionosphere? Let's end our exploration of the mysterious moons of our solar system by getting a little closer to Earth. We're on our way to Mars and its two moons, Phobos and Deimos. These two moons share many characteristics with C-type asteroids, primitive bodies dating back to the genesis of the solar system. But contrary to what researchers have long believed, these are not primitive celestial bodies that were attracted to Mars from the asteroid belt like Triton. Not only is Mars' gravitational pull too weak, but their orbits are too circular. Phobos and Deimos are more likely to be the result of a collision between Mars and a giant celestial body. Perhaps these two moons were born at the same time, but their trajectories are different. Phobos is approaching Mars by around 2 meters every 100 years, while Deimos is moving away. In fact, Phobos is the closest satellite to its planet in the entire solar system. Its surface is dotted with craters, fissures, and other marks left by meteorite impacts. According to the researchers, Phobos will be destroyed in 30 to 50 million years due to deformations caused by Mars's tides and gravity, while Deimos will probably move away and emancipate itself from Mars' gravitational pull. In any case, these two moons are unlikely to harbor life. In the quest for extraterrestrial life, it's Mars that interests researchers. Europa, Ganymede, Callisto, Titan, Enceladus, Triton. All these moons could be inhabited by forms of life we can't yet imagine. Research carried out in recent years on the moons of our solar system has shown us that there are worlds not so far away from us that are very different from our own, and yet could be home to extraterrestrial life forms. But is life on these seemingly cold and hostile moons possible? On Earth, we've discovered that life can cope with far more extreme conditions than previously imagined. Some microbes can live in arid deserts, in lakes saturated with arsenic, or on the walls of caves dripping with sulfuric acid. Environments that are toxic for us can be conducive to the development of other types of living beings, ultra-resistant organisms, unsuspected forms of life. Everywhere on Earth, life manages to thrive. So why not in underground oceans, sandwiched between several layers of ice and maintained in a liquid state by an internal energy source? Recent discoveries have prompted researchers to rethink their models and re-examine what they already know. Worlds that had previously been considered too hostile are now being re-examined and analyzed from a different angle. Whereas before, the search was for Earth-like planets, the field of possibilities has been broadened by looking at other types of celestial bodies, which offer other conditions and environments, and which may favor different types of chemical processes, with a result that could well be life. We're going to start this journey with one of the best-known supervoids. We're about 700 million light-years from Earth, in the constellation of Bouvier. You're looking at one of these supervoids, the gigantic, several hundred million light-year wide voids found throughout the universe. Its name, the Bouvier Void. With a radius of 165 million light-years, the Bouvier Void is one of the largest known voids, though not the largest. It's also known as the Great Void. The Bouvier Void is over 330 million light-years wide, but contains only around 60 galaxies. And yet, in such a volume of space, we would normally find tens of thousands of galaxies. After all, these 60 or so galaxies are spread over a volume of space 2.5 times larger than that of the Virgo supercluster, which itself contains over 10,000 galaxies. Needless to say, these few galaxies are very far apart and therefore very isolated. So much so that according to American astronomer Greg Aldering, if the Milky Way were at the center of the Bouvier Void, we wouldn't have known that other galaxies existed until the 1960s. This supervoid was discovered by American astronomer Robert Kirshner and his team in 1981 during a survey of galaxy redshifts. The astronomer detected a strange anomaly in a region of space located in the constellation du Bouvier. He couldn't believe his eyes. Incredible as it may seem, this region of space appeared to be empty. This super-emptiness was named the Bouvier Void after the constellation in which it lies. Shortly afterwards, galaxies were discovered in this region of emptiness. By 1987, 8 galaxies had been discovered. 3 more were discovered the following year. By the end of the 1990s, the Bouvier Void was considered to contain just 60 galaxies, which still makes it, from a relative point of view, a strangely empty zone. Astrophysicists were quick to seek explanations for this anomaly. Among the theories put forward to explain this supervacuum, one in particular has caught the attention of the scientific community. What if supervoids were in fact formed by the aggregation of smaller voids in the manner of soap bubbles coalescing to form larger ones? This theory has never been confirmed. In fact, few scientists today believe it to be the correct explanation for the formation of supervoids. Be that as it may, the Bouvier Void has become the best-known supervacuum, even if other voids of even more impressive dimensions have subsequently been discovered. One of the reasons for its popularity is that it contains the most isolated spiral galaxy ever discovered. This galaxy, which was observed by Hubble, is called MCG plus 01-02-015. It lies in the constellation of Pisces. Although the Bouvier Void is located in the constellation Bouvier, part of the void lies in the constellation Pisces. The galaxy MCG plus 01-02-015 lies at the center of this void, on the border between the two constellations. And around it, no galaxy has been identified for 100 million light-years, no matter which direction the scientists observed. The Bouvier void made news again recently in September 2023 with the discovery of an astonishing structure described as a bubble of galaxies. This bubble of galaxies appears on images as a spherical shell with a core composed of a supercluster of Bouvier galaxies, surrounded by the Great Bouvier Void, and girdled by other superclusters and galactic filaments, such as the Great Sloan Wall. This structure is colossal in size. It has been estimated to be 1 billion light-years across, or 10,000 times larger than our galaxy. According to a study published in the Astrophysical Journal, its genesis dates back to the earliest days of the universe, some 13.8 billion years ago. This impressive structure is located 820 million light-years from the Milky Way, in what astronomers call the near universe. It has been christened Ho Oleilana, a Hawaiian word meaning whispers of awakening, found in the Hawaiian Song of Creation. The name was given by the study's first author, Richard Brent Tully, an American astrophysicist from the Institute of Astronomy in Honolulu. Tully was responsible for another major discovery in 2014, that of the galactic continent that came to be known as Laniakea, Hawaiian for immense sky. The discovery is part of a very long scientific process, as it validates a phenomenon that was described in 1970 by Jim Peebles, an American cosmologist who later won the Nobel Prize in Physics. He postulated that the processes that govern the primordial universe, then made up of a plasma of particles and light, produced acoustic waves whose vibrations created bubbles with matter at the center. This process was interrupted 380,000 years after the Big Bang, freezing the shape of these bubbles. Then, driven by the expansion of the universe, these bubbles grew. This phenomenon, known as baryonic acoustic oscillation, had not yet been directly proven. In 2005, statistical analyses of galaxy catalogs had indirectly proven the existence of this phenomenon, but this is the first time that this bubble of galaxies has been directly observed. In addition to validating Jim Peebles' postulate, this discovery has helped to adjust the value of the Hubble constant. This constant is very important in cosmology, as it is used to calculate the expansion rate of the universe. But its values differ depending on whether it is measured in the near or distant universe, which complicates matters. The discovery of Ho Oleilana confirms the first value, the one applied to measure the expansion of the universe in the near universe. The discovery of this first bubble of galaxies opens a new chapter in astrophysics. New instruments such as the European Space Telescope Euclid, launched in July 2023, or the large South African radio telescope, SCA, will contribute to a better understanding of the expansion of the universe, and perhaps the discovery of new galaxy bubbles like Ho Oleilana. The Bouvier void was not the first void to be discovered. In fact, the first cosmic voids were discovered in 1978 by two astronomers from the American Kitt Peak Observatory in Arizona, Stephen Gregory and Laird Thompson. You may be wondering why void zones weren't discovered earlier, when they seem so obvious today. Quite simply, because to detect a void, you first have to map the space in which it exists. For a void is defined first and foremost by its boundaries. which are the filaments formed by the clusters of galaxies that have gathered in clusters around these voids. So, to detect the voids, we first had to map the sky, or at least the regions of the sky in which these supervoids are found. And to map the sky, it was first necessary to establish a catalog of galaxies. Once this catalog had been established, an algorithm could isolate and count the voids. For example, several hundred voids could be detected from a single survey of 1 million galaxies carried out between 2009 and 2014. By mapping the sky, astrophysicists were able to highlight areas of cosmic void, or rather, regions apparently devoid of galaxies. The voids thus discovered vary greatly in size, but they are all rather immense. To give you an idea, the smallest voids detected are a few million light-years across, 10 times larger than our own Milky Way galaxy, which is only 100,000 to 200,000 light-years across. It's important to remember that back in the late 1970s, when the first voids were discovered, cosmological models were not the same as they are today. There were still very few surveys of galaxy distribution. Moreover, it was not yet known whether galaxies were homogeneously distributed or organized in structures. It was then, with the first systematic surveys of galaxies, that scientists had the first evidence of the spatial structuring of galaxies, and with it, the first evidence of the existence of void zones. The discovery of cosmic voids at the end of the 20th century was a major step forward in establishing the current cosmological model. But we were still in the early stages of studying these mysterious voids. And today, the mysteries raised by the discovery of voids in our universe are far from being solved. At the end of the 70s, astrophysicists thought they had hit the nail on the head without suspecting that the discovery of the spatial structuring of galaxies would raise other, ever more complex questions. What was revealed by the first galaxy surveys, these large structures of galaxy filaments surrounding cosmic voids, is what we now call the cosmic web. Look at this image of our universe. Doesn't it look like a big spider's web from up here? The filaments formed by the galaxy clusters are the spider's web, and the gaps are the holes in the web. In any case, scientists have found this image a telling one, and it's now the term used to designate the spatial structuring of galaxies and voids in the universe. Like in a spider's web, holes or voids are everywhere, in every direction. In other words, our universe is riddled with voids. Everywhere you look, you can see voids. Does this surprise you? Well, it's only natural. The mapping of our universe in dynamic or 3 dimensions has taught us that photographs taken by telescopes like Hubble in 2 dimensions can be misleading. Take this image of the sky, reconstructed from Hubble telescope data. You can see multiple points of light, which are the stars and galaxies, but you can't tell from this single image the distances between galaxies. You may have the impression that these galaxies are all on the same plane, but in reality, many of the bright dots are in the foreground, and the rest are in the background, several 100 million light-years away from the foreground objects. The dots also appear luminous because among them are distant stars or galaxies that shine brighter than those in the foreground. See where we're going with this? The images we marvel at every day give us a misleading view of our universe because they don't tell us how these galaxies are distributed in 3 dimensions. Before the discoveries made at the end of the last century, astronomers believed that all galaxies were uniformly distributed throughout the cosmos. It's only recently that we've discovered that over time, under the influence of gravitation and the expansion of the universe, galaxies agglomerate into clusters and superclusters, taking the form of a vast cosmic tapestry. This cosmic tapestry is made up of spaces rich in matter and spaces that are almost devoid of it, voids, great voids, or supervoids. The Great Void of the Bouvier is just one among many. Thousands of other voids have been cataloged since the late 70s. In fact, there are more voids than there are matter-rich zones. 90% of the volume of our observable universe is made up of voids. It's the void that runs the show, defining the shape of the cosmic web. But let's stop for a moment before continuing our journey to clarify what we mean by void. Is the cosmic void, that which corresponds to the holes in our vast cosmic web, an absolute void? Let's remember that an absolute vacuum is the absence of matter. It's a space in which there's nothing, no particles, it's nothingness. Let's also remember that the vacuum isn't necessarily a space where you can't see anything. Take air, for example. Try moving your hands quickly. You can feel air particles brushing against your hands as they move through the air. Air is not empty. It contains particles that you can't see with the naked eye, but which are definitely there. In fact, when we breathe in, we inhale billions of molecules. Just because you can't see anything in a space doesn't mean it's empty. So is there such a thing as an absolute vacuum? On Earth, it would seem not. As long as there's atmospheric pressure, there's matter and particles. But on Earth, everything is subject to atmospheric pressure and universal gravitation. What about space? Beyond the stratosphere, atmospheric pressure is virtually non-existent. In fact, it's so low as to be imperceptible to human beings. But it exists all the same, and our scientific instruments can measure it. When astronauts leave the International Space Station, they don't feel that there are air particles all around them. And yet there are. The International Space Station orbits the Earth fast enough to be micro-resisted by the atmosphere, so that it has to readjust its trajectory every 3 months to maintain its orbit. Proof that there's something beyond the stratosphere. According to a recent study involving the CNRS, the atmosphere is measurable up to an altitude of 630,000 kilometers or 390,000 miles. A phenomenal distance, given that the Moon lies between 356,000 and 406,000 kilometers, or 220,000 and 250,000 miles from us, depending on its position in the ellipse it describes around the Earth. This means that the Moon's orbit still contains hydrogen atoms from the Earth's atmosphere. You'll agree that we can't speak of an absolute vacuum. As long as there are atoms, there is no vacuum. However, astrophysicists speak of the vacuum of space. It's important to differentiate between the absolute vacuum and the vacuum of space. Beyond the stratosphere, pressure is so infinitesimal that we can speak of the vacuum of space. The vacuum is not absolute, but it is relative. In relation to the Earth, space beyond our atmosphere appears empty. Let's take a look at some figures to better understand what we mean by a relative vacuum. The CNRS states that at an altitude of 60,000 kilometers, or 37,000 miles, the atomic density is 70 atoms per cubic centimeter. This is very low. On Earth, there are 53 billion molecules per cubic centimeter of air, and twice as many atoms. And yet, it's still higher than the atomic density of the so-called interplanetary vacuum. As a general rule, the higher you go above sea level, the thinner the air becomes, and the lower its atomic density. At an altitude of 10 kilometers or 6 miles, it is divided by 4 compared with sea level. In the interstellar medium, atomic density drops to 1 atom per cubic centimeter, and in the intergalactic medium, it can fall to less than 10 atoms per cubic meter. And yet, these intergalactic environments, poorly dense though they may be, are said to contain around half the mass of the universe. What does all this tell us? There are several types of cosmic void. The interstellar void, for example, is 100,000 times denser than the intergalactic void. But as human beings, we're unable to perceive any difference between the atomic density and the altitude of the International Space Station at 400 kilometers or 250 miles, and that at the level of the Moon's orbit, or even that of intergalactic space. For us, it's a vacuum, and it's still not absolute vacuum, it's relative vacuum. These spaces are less dense than the space we live in, so they appear empty to us. Let's take another example to understand the difficulty of finding absolute emptiness. This is a famous scientific experiment carried out by Otto von Guericke, Burgomaster of Magdeburg, on May 8, 1654. The experiment remains famous not only because it completely baffled Emperor Ferdinand III, but also because it was one of the first scientific experiments to feature the vacuum. Here's how the experiment went. The German scientists laid 2 hemispheres against each other to form a perfect ball, then attached 2 ropes to these hemispheres, connected to 2 teams of 15 horses. Together, the horses pulled on their carriages to lift the 2 hemispheres off the ground, but they never succeeded. And yet, these hemispheres were not glued together with superglue. In fact, thanks to a valve system, Otto von Guericke had removed the air from the sphere, keeping the 2 hemispheres glued together by the pressure difference between the outside and inside of the theoretically empty sphere. To get the 2 hemispheres off the ground, you simply had to open the valve, or exert an action with a mass equivalent to 2.5 tons. This experiment was one of the first to create an artificial vacuum and observe its properties. It's a bit like the candle experiment, which you can repeat at home. Put a candle in a glass and place a second glass upside down on top. Once all the oxygen has disappeared, the 2 glasses stick together. So are we talking about absolute vacuum in these 2 cases? No, not really. Rather, it's the kind of vacuum we find at the altitude of the International Space Station, for example. If it were an absolute vacuum, the force required to separate the 2 hemispheres, or the 2 glasses, would be infinite. Would an absolute vacuum be impossible on Earth or in the universe? Let's see what the theory tells us. Let's imagine a cube where we've succeeded in obtaining a complete vacuum of matter. To maintain such a vacuum of matter, several things are required. Firstly, the walls of the cube must be completely opaque to electromagnetic radiation across the entire spectrum. Secondly, the walls of the cube must not produce or transmit any heat. This ensures that no matter can enter the cube. Let's imagine such a cube where there are no atoms or photons. Is it an absolute vacuum? Not yet. In the universe, we find particles that interact little with matter, such as neutrinos. These particles, however, could pass through the walls of the cube, because even if they interact very little with matter, they interact all the same. Theory tells us that it would be possible to stop neutrinos, but to do so, the cube would have to be surrounded by a lead wall, a light-year thick. In practice, this is impossible. The structure would collapse into a black hole, further proof that the vacuum in the cube is not absolute. Yes, because even without atoms, photons, or neutrinos, the cube remains occupied by the gravitational field. This is a fundamental property of the universe. Any massive object creates a gravitational well with an infinite range. In theory, even a speck of dust 10 billion light-years away would have a gravitational influence on our solar system, although in practice, this influence is masked by that of closer, more massive objects. The cube cannot escape this fundamental property of the universe, so it will never be empty. Some theories go even further, arguing that gravitation is transmitted by a particle known as the gravitator. The cube of our experiment would therefore be filled with these gravitants. And even if we consider that the quantum gravitational fields present in this cube are at their lowest level, there will always remain what we call vacuum energy. Vacuum energy is an underlying energy that exists everywhere in space throughout the universe. It is the energy of a zero point where the physical system contains no matter. In quantum field theory, vacuum energy is not empty space. It's the fundamental state of fields. Even more astonishingly, the smaller the volume considered, the greater the vacuum energy. Vacuum energy can be explained by virtual particles, which appear and then annihilate in such a short time that they cannot be observed. These virtual particles would be present throughout the universe. The theory of vacuum energy is not random. It would explain several phenomena, such as spontaneous emission, the Casimir effect, and the Lamb shift. These are quantum phenomena that we won't go into now, but which would influence the behavior of the universe on a cosmological scale. Still not convinced by all these demonstrations? There's another irrefutable proof that the absolute vacuum doesn't exist. The vacuum isn't static, it's expanding. And something that's expanding can't really be empty. You've got it right. There's no such thing as an absolute vacuum. But then, when we talk about voids and supervoids, what are we talking about? The vast regions of emptiness we observe in our universe are not devoid of all matter. As in the Bouvier void, galaxies can be found there, albeit extremely scattered over a gigantic area. Supervoids are not empty in the sense that there is nothing there, but empty because they are much less dense than the rest of the universe. These regions of cosmic emptiness are at least 10 times less rich in galaxies per unit volume than our galaxy clusters. We can therefore define the void in the universe as an area where the density is 10 times lower than the average of the observable universe. According to the dark energy hypothesis, cosmic voids would contain less matter than the rest of the universe, but they would still contain something: dark energy. Physicists have estimated that nearly 70% of the universe's energy content is due to this component, which is neither matter nor radiation. Dark energy has never been directly observed. It is therefore a hypothetical form of energy. Although the nature of dark energy is still unknown, it is necessary to interpret the observations made by scientists, first and foremost, the acceleration of the cosmological expansion. It could be a cosmological constant or a cosmological object in its own right, for example. In any case, its existence is not forbidden by the theory of general relativity. But how did astronomers come to suppose the existence of such a mysterious energy permeating our universe? It all began with the discovery that the universe was expanding. In the 1920s, Russian physicist Alexandre Friedmann and Belgian physicist Georges Lemaitre laid the theoretical foundations for the expansion of the universe, based on Einstein's general relativity. At the same time, American astronomer Edwin Hubble observed that the greater the distance between galaxies, the faster they were moving away from each other. This observation gave rise to Hubble's law in 1929. Hubble's law describes the expansion of space-time itself, not the motion of galaxies in the universe. It was also in the mid-1920s that the Big Bang theory was born. Today, this theory forms the basis of the cosmological model most widely accepted by the scientific community. What does it say? According to the Big Bang theory, the universe was extremely dense and hot 13.8 billion years ago. Over the ensuing billions of years, it has evolved. It is expanding, but it is also being slowed down by the attractive force of gravity. In 1998, research teams revealed an inconsistency with this model. The light received from distant supernovae was weaker than expected. To explain these curious observations, the researchers assumed that there was some kind of vacuum energy, which had been accelerating the expansion of the universe for almost 6 billion years. This is when the concept of dark energy was born. Today, we still can't explain with any certainty why the universe is accelerating. This is why dark energy remains hypothetical. This component of the universe, unlike the gravitational force, would act as a repulsive force. Two hypotheses have been put forward. According to the first hypothesis, the density of dark energy may remain constant over time. Dark energy would then be a fundamental constant of nature, or what we call a cosmological constant. It can then be added to the equations of Einstein's general relativity. According to the second hypothesis, dark energy density could vary over time. If this hypothesis were confirmed, Einstein's theory would have to be revised in greater depth. And like all hypotheses, the concept of dark energy can also be wrong. We're now off to discover several of the great voids that surround us. Two supervoids are particularly close to us: the local void and the boreal superlocal void. The local vacuum is so called because it lies right next to our local group, or at any rate, very close on the scale of the universe, for it has been estimated that the local void lies 75 million light-years from our planet. This virtually galaxy-free region was discovered by Richard Brent Tully and Rick Fisher in 1987. While its dimensions are unknown, researchers believe that the void is at least 150 million light-years wide and possibly up to 230 million light-years long. This void is divided into 3 sectors separated by points of vaporous filaments. As we've seen, voids are the result of the way gravitation causes matter in the universe to attract and clump together. Gravitation groups galaxies into groups and clusters, and separates them from regions that are almost entirely empty of galaxies. Our Milky Way lies at the heart of a wide, flat row of galaxies known as the local veil. This filament delimits the local void. The image of a raisin bun is often used to represent the expansion of the universe. Imagine a raisin bun baking in the oven. The brioche is the universe. It expands as it bakes. The raisins are the galaxies. As the bun expands, they move away from each other, but remain unchanged. We could add a third component to this telling image of the brioche with raisins. The air bubbles represent the voids. As the brioche bakes, or as the universe expands, the air bubbles swell, just as the voids grow. Scientists believe that the local void is growing, and that the local veil is moving away from the center of this void at a speed of 260 kilometers per second, or 160 miles per second. Concentrations of matter attract each other, creating a larger void from which matter can escape. Indeed, the larger the vacuum, the emptier it is. The emptier the void, the weaker the gravity. An isolated dwarf galaxy within the local vacuum could therefore escape the vacuum and move towards concentrations of matter. But this phenomenon can also be explained by the effect of dark energy. A model was proposed a few years ago, according to which there is a relative vacuum centered on the Milky Way. In other words, we too are in a zone of relative vacuum. This model, known as the Hubble bubble, caused quite a stir, and is still defended by some scientists, although it has never been confirmed. If this model were true, then the entire cosmological model on which our understanding of the universe is currently based would have to be revised. We have based our cosmological model on the principle of homogeneity and isotropy. We believe that our universe is homogeneous and isotropic, meaning that it's the same, no matter which direction you look in. From our point of view, we can understand the universe as it is. This principle of homogeneity and isotropy assumes that we do not occupy a particular position in the universe. This is the so-called Copernican principle. The Copernican model is opposed to the geocentric and heliocentric models that have prevailed since antiquity. According to the geocentric model, the Earth was immobile at the center of the universe, and the planets around the Earth followed complex trajectories on epicycles. When it was discovered that the Earth revolved around the Sun, the heliocentric model replaced geocentrism. This time the Sun was at the center of the universe, and the planets followed circular trajectories. This model was disseminated by Copernicus, then expanded by Galileo, who discovered that the planets formed ellipses around the Sun, not circles. Now we know that the Sun is no more at the center of the universe than the Earth is. In fact, the Sun is a star like any other. It lies among at least 100 billion other stars in our galaxy, just as our galaxy is one of some 200 billion galaxies in the observable universe. This more realistic model is the one that prevails today, but it raises questions and forces us to invoke an accelerated expansion of the universe, and therefore the existence of dark energy. That's why some physicists have gone so far as to question this basic postulate. What if we found ourselves in a region of the universe slightly less dense in galaxies than the rest of the universe? In other words, in a region of relative vacuum. This hypothesis would explain our perception of accelerated expansion without the need to invoke some form of new energy to explain this movement. This is the Hubble bubble. If the Earth is at the center of a relative vacuum, there is a denser material around this vacuum that attracts matter away from the central point of the vacuum, in the same way that the local veil attracts dwarf galaxies isolated from the local vacuum. In other words, the stars around us are being pulled away from Earth much faster than the speed of the universe's expansion, which explains the acceleration of the universe's expansion. The Hubble bubble would also explain why the two methods used to measure the Hubble constant do not give similar or even reconcilable results. The Hubble constant is a measure of the speed of expansion of the universe, or more precisely, the ratio between the distance and recession velocity of galaxies in the universe. If the Copernican principle is true, then this speed is constant. Wherever it is measured in the universe, we should obtain the same value. But this is not the case. The first method used to measure the Hubble constant uses the cosmic microwave background as a benchmark, while the second is based on supernovae, which appear sporadically in galaxies and are easily observed by their brightness. But the data obtained with these two methods are quite different. The first method gives a value of 67.4 kilometers, or 42 miles per second, per megaparsec, which means that the universe expands by 67.4 kilometers, or 42 miles per second faster every 3.26 million light years. The second method gives a value of 74 kilometers per second per megaparsec, or 46 miles per second per megaparsec. One more mystery to solve in the quest to understand our universe. The Hubble bubble hypothesis, like the dark energy hypothesis, remains unproven. But in any case, it's true that we're evolving in one of the least dense regions of space. If we consider the void to be a volume of space within which matter is significantly less present than it is on average in the rest of the universe, then our planet lies in a void 7 times larger than the average. A void that stretches for almost 2 billion light-years and encompasses our galaxy and thousands of others around us. It's called the KBC vacuum. Astronomers Ryan Keenan, Amy Barger, and Lennox Cowie named this supervacuum after studying it in 2013. This void, or underdensity zone to be more precise, takes roughly the shape of a sphere 2 billion light-years across. This near-empty zone includes not only the Milky Way, but also the local group and most of Laniakea. As for us, we're just a few 100 million light-years from the center of the void. The KBC void may be less empty than the Bouvier or local voids, but it is still very sparse compared with the average of the universe. It's hard to imagine that the region of sky in which we find ourselves can be considered a vacuum. After all, the KBC void is home to the Milky Way and the local group, a group of more than 60 galaxies, including our own, stretching over a diameter of 10 million light-years. The local group may not be the most impressive cluster of galaxies, but it contains at least one other massive galaxy in addition to the Milky Way, the Andromeda Galaxy, or M31. Like the Milky Way, this is a spiral galaxy. It is even more massive than our galaxy, with a diameter of 220,000 light-years, and contains 1,000 billion stars, which has led to it being mistaken for a nebula. These two galaxies are not isolated. They are separated by around 2.5 million light-years, which is still close on the scale of the universe. In fact, they are so close that in 4.5 billion years' time, they will collide. Our galaxy and the Andromeda Galaxy are approaching each other at over 400,000 kilometers per hour, or 250,000 miles per hour. The KBC void also contains the Virgo cluster, a gigantic cluster of galaxies comprising 1,300 to 2,000 galaxies. Larger than the local group and its 60 or so galaxies, the Virgo cluster is but a drop in the ocean next to the Virgo supercluster, also contained in the KBC void. The Virgo supercluster, or local supercluster, encompasses the Virgo cluster at its center and the local group. We could go on and on. The KBC void contains a good part of Laniakea, a veritable galactic continent that encompasses not only the Virgo supercluster, but also the Hydra Centaur supercluster and the Indian Peacock supercluster. So maybe for you it's not a void, but for scientists this area can relatively be described as a void. The discovery of this near-vacuum zone has been the subject of much debate. The question is whether its existence is compatible with the current cosmological model, the standard Big Bang model, also known as the concordance model, or lambda CDM. CDM stands for cold dark matter. This model is the most widely accepted because it is the simplest model that can account for the properties of the observable universe. In other words, it's the only model that can provide a simple explanation, not only of the existence and structure of the cosmic microwave background, but also of the large-scale structure of galaxy distribution and the expansion and acceleration of the universe. It is also the simplest model to explain the abundance of nucleons and light elements in the universe, such as hydrogen, helium, and lithium. This model assumes that the theory of general relativity correctly describes gravity. It emerged in the late 90s at a time when the scientific community was struggling to find a consensus on the composition of the universe's energy densities. Some scientists believe that the KBC vacuum cannot exist in the universe as described by this model, but others believe that such a supervacuum, however immense, is entirely consistent with this model. The debate is still going on. In concrete terms, what difference does it make to us to know that we're at the heart of a zone with a density well below the average for the universe? For scientists, a great deal, as it may explain, for example, why we have a higher local Hubble constant. For us, not much apart from the fact that our night sky is slightly darker than on other planets located in other parts of the universe. Let's continue our exploration of supervoids. Richard Brent Tully and his team have not only discovered the local vacuum, they have also discovered another supervacuum close to us, the Boreal local supervacuum. This vacuum is called a supervacuum because it extends over a diameter of 339 million light-years. In this area, no rich clusters of galaxies have been identified. The center of the local Boreal supervacuum is located 199 million light-years from the Milky Way, between the Virgo supercluster and the Hercules supercluster, between the constellations of the Bouvier, Virgo, and Snakehead. Along with the Virgo supercluster, the Hercules supercluster is one of the three most important superclusters in Laniakea. As you may have guessed from its name, it lies in the constellation of Hercules. This supercluster is actually made up of two interconnected galaxy superclusters. The larger one contains several rich clusters, including A2147, A2151, and A2152, and hundreds of small groups of galaxies. The second supercluster is dominated by two galaxy-rich clusters, A2197 and A2199. Together with the Virgo supercluster, this Hercules supercluster defines the boundaries of the Boreal local supervacuum. Now it's time to step back a little and explore the Eridan void. This supervacuum is probably the largest known. Located in the constellation Eridan in the southern hemisphere, this supervacuum was identified by researchers at the University of Hawaii at Manoa on April 21, 2015. According to researcher Istvan Sapudi, who led the research, it is the largest structure ever identified by mankind. This immense void is said to measure 1.8 billion light-years in diameter. Like the local void and the Boreal local supervoid, the Eridan void is not so far from us. It lies just 3 billion light-years from Earth, which may seem enormous to you, but remains relatively short in the immensity of the universe. How was this supervacuum spotted? We've already seen that it's rather difficult to spot voids in the sky. Astronomers will first concentrate on what they can see, before turning their attention to what they can't see. The Eridan void was spotted thanks to Hawaii's Pan-STARRS 1 telescope. It all began in 2004, when scientists noticed the presence of an anomaly, thanks to data recorded by the Wilkinson Microwave Anisotropy probe. The anomaly is a cold spot, in stark contrast to neighboring regions with milder temperatures. The term cold spot refers to a gigantic zone, colder than the rest of the surrounding universe, a veritable oil stain in the uniformity of the universe. To better understand why this discovery astonished the scientific community, we need to go back to the very beginnings of our universe, the famous Big Bang. For a time, the young universe was a soup of electrically charged particles that held light captive. This is known as the dark ages of the universe. When the first atoms were formed, light was released. The cosmic microwave background is a remnant of this dark age. It is normally fairly homogeneous, with the exception of the famous cold spot. Many hypotheses have been put forward to explain this cold spot. Had another universe been discovered? Had we made a miscalculation? Was it a black hole? The answer was simpler. It was in fact a supervacuum, the Eridanus supervacuum. Scientists hypothesized that there was such a huge void there that it slowed down the power of light, and therefore the circulation of heat. As they pass through the void, light rays gradually weaken, and in the case of such a supervacuum, it takes hundreds of millions of years for light to travel through it. But then scientists realized that the vacuum itself couldn't be the only explanation for the coldness that had been detected. Voids aren't really empty, they're simply less dense than the rest of the universe. According to Andres Kovacs, a scientist involved in the study, the Eridanus supervacuum contains around 20% less matter than our part of the universe. This means there are almost 10,000 galaxies missing from this part of space. This may partly explain its unusually low temperatures, but only partly, for the mystery is far from solved. Scientists are now seeking to understand how the vacuum formed itself. Here again, dark energy may well have a role to play. However, the hypothesis of a parallel universe has not been definitively ruled out. Some scientists believe that this cold spot could be proof of the presence of parallel universes. Some even support the controversial hypothesis that there are billions of universes just like ours. The Eridanus supervacuum would then be the result of a collision between two universes. Laura Mersini-Houghton, cosmologist, theoretical physicist, and professor at the University of North Carolina at Chapel Hill, is one of the scientists who support the parallel universes hypothesis. In her view, standard cosmology cannot explain such a gigantic cosmic hole. This cold spot in the universe would therefore probably be the imprint of another universe beyond the edge of our own, caused by quantum entanglement between universes before they were separated by cosmic inflation. The theory of cosmic inflation describes the extraordinary expansion of the universe at the time of the Big Bang, which kick-started the formation of the universe as we know it today. The universe underwent a very rapid expansion phase, enabling it to swell by at least 10 to the 26th power in the extremely short time after the Big Bang. At that point, space expanded faster than the speed of light, and the universe doubled in size by at least 90 times, going from subatomic to golf ball size almost instantaneously. Then all the other forces were formed in just a fraction of a second. Neutrons and protons formed, then fused, creating hydrogen and helium nuclei. 380,000 years later, these hydrogen and helium nuclei captured electrons to form atoms, and the foundations of our universe were laid. This theory of cosmic inflation has convinced some researchers that it's entirely possible that there are other universes parallel to our own. According to theoretical physicist Alexander Vilenkin of Tufts University in Massachusetts, cosmic inflation did not end at the same time everywhere. So yes, it ended for everything we can detect from Earth 13.8 billion years ago, but it continues in other places too. This is known as the theory of eternal inflation. When cosmic inflation ends in one place, a new bubble universe is formed, and so on. The multiverse theory may be one of the most controversial in science, but it is supported by many scientific theories today. Perhaps the study of the mysteries of the supervacuum will enable us to find out more in the decades to come. Let's continue our exploration of the supervoids of our universe. Less well known than the local void, the Bouvier void or the Eridanus void, the giant void is located in the Hound constellation. It's also known as the Hound supervoid, or ARLP36. After the Eridanus void, it is the second largest void confirmed to date, and the largest in the northern hemisphere. Its diameter ranges from 1 to 1.3 billion light-years. The center of the void is located 1.5 billion light-years away. This supervacuum was discovered in 1988. It contains 17 galaxy clusters concentrated in a spherical area. These galaxy clusters have no interaction with each other, which shows that the density of the clusters is very low. Understanding the properties of the cosmic vacuum is one of the challenges of modern science, because, paradoxical as it may seem, the study of vacuums can provide us with a wealth of information about our universe and its history. Because the origin of these supervoids lies in remote times, the study of voids can first help us understand the formation of our universe and the rules that have governed its evolution. It would seem that in the primordial universe, small irregularities, small variations in density, were formed and then amplified to become the immense zones of relative vacuum we know today. Studying voids will enable us to understand how these zones of density, which form the galaxies, and these zones of subdensity, which gave rise to these immense voids, were formed. Studying voids will also help us understand how the great structures of our universe were formed. Is it because of their presence that galaxies group together in clusters and filaments, forming the cosmic web we see today on dynamic maps of the observable universe? Or, contrary to popular belief, are voids the consequence of the structuring of galaxies into clusters, superclusters, and then filaments of matter? But above all, the study of voids could also provide us with the information we're lacking on the famous dark energy that lies behind the expansion of the universe. Dark energy would explain why the expansion of the cosmos has been accelerating for some 7 billion years without our having to modify Einstein's laws of general relativity. But its existence remains hypothetical, and scientists are still looking for real evidence to validate its existence. Supervoids are the ideal laboratory for testing models of dark energy and modified gravity, which would replace general relativity. Cosmic voids, which make up 90% of the volume of the universe, contain very little matter and could be composed mainly of dark energy. Logically, these are the first elements to be observed if we are to find evidence of the existence of this mysterious energy. Studying cosmic voids is also a good way for scientists to measure the evolution of the expansion of the universe. Let's imagine we're trying to compare the apparent extent of a void in depth with its extent on the sky. The former is given by the speed at which the galaxies that delimit it are moving away, and the latter by the distance on the sky between these galaxies. According to the cosmological principle that the universe is homogeneous and isotropic, cosmic voids should resemble balls. These two expanses are then equal on average. This property enables us to measure the speed of expansion at the instant when light was emitted by the galaxies, delimiting the cosmic void, and thus to learn more about the contents of the universe at that time. The vacuum is one of the structures that enable us to measure the expansion of the universe, but there are others, such as the acoustic oscillations of primordial plasma, structures even more immense than supervoids. Voids form a ball, but this is only true on average. In reality, their individual shapes can vary and even be highly complex. That's why voids are so difficult to identify. In 2007, algorithms based on these principles were published. In a way, they are databases that help us to better understand the universe. They can identify voids, even when there are small distortions in the spatial distribution of galaxies. Scientists have also created an analysis chain called VIDE, which has made it possible to build open databases of cosmic voids from the Sloan Sky Survey. Subsequently, other catalogs of cosmic voids were built from other surveys. Scientists realized the importance of mapping not just galaxies and galaxy clusters, but voids too. Today, advances in technology enable ever finer analyses of the data collected. Galaxy surveys are becoming more and more comprehensive, and we are now able to detect more voids and reconstruct the cosmic web as faithfully as possible from galaxy surveys alone. And so, little by little, supervoids are beginning to reveal their secrets. A recent study by researcher Nico Hamas from the University of Munich investigated the speed of galaxies within voids. A challenge in itself, since the speed of a galaxy is not so easily measured. Two components have to be averaged. The first is the speed associated with the expansion of the universe, the redshift, which causes galaxies to move away from the Milky Way. The second component is the galaxy's own speed within the vacuum. And then there's the gravitational attraction exerted by the dense matter regions bordering the void. Thanks to their measurements, Nico Hamas and his team have been able to estimate the average density of matter in the universe and the growth rate of large structures. The eBOSS program, an extension of the BOSS program, and the Euclid observations will enable us to observe over 10 billion objects, including 50 million galaxies. With such a catalog, there's no doubt that we'll be able to discover new supervoids and continue to unravel their mysteries. In short, the study of vacuums can provide us with many new insights into our universe and its secrets. The next step in the study of voids is to identify voids that are ever more distant from us. For the more distant regions of the sky we observe, the younger the universe becomes. Observing distant voids will enable us to understand the dynamics of dark energy, its evolution, and its role in the history of the universe. Above all, it will allow us to test hypotheses, validate models, and move forward in the quest to understand our universe. Here's an image of the so-called pillars of creation in the Eagle Nebula, or NGC 6611. These columns of interstellar dust are in fact a star-forming zone at the heart of one of the most productive star-forming zones in the Milky Way. This photo dates back to 1995. It was taken by the Hubble Space Telescope, the predecessor of the James Webb, which was launched in 1990. Now take a look at this photo, taken in October 2022 by the NIRCam infrared camera of the James Webb Telescope. The difference is striking. It's like putting on glasses for the first time. A second image was taken by the James Webb's MIRI instrument, the only one that can see in the mid-infrared. This image is darker, and the stars can't be seen as clearly as in the first image, but it's still very impressive. It's the infrared vision of James Webb's instruments that allow us to see through the clouds of gas and dust and distinguish all these stars. The image is so detailed that it's easy to interpret. You can clearly see red dots representing baby stars, only a few 100,000 years old, and red streaks in the clouds of dust and gas that are actually nascent balls of gas that will later become stars. There's no shortage of examples of images that have been recaptured by the James Webb with greater sharpness and precision than those taken by Hubble. Why? Because the James Webb, unlike Hubble, observes the universe in the infrared. This enables it to capture the rays of the first stars, which were emitted in ultraviolet form, but whose wavelengths, stretched by the expansion of the universe, then shifted towards the red. The more pronounced the red shift, the more distant and ancient the star. Between May and September 2023 alone, the James Webb produced an impressive number of images of stunning sharpness and detail. Colliding or merging galaxies, stellar nurseries, gigantic black holes, magnificent nebulae. The Space Telescope lets us see what we can never see with the naked eye, not only because it's too far away, but also because our eyes can't see in these wavelengths. These images will undoubtedly help us to better understand the genesis of the universe, but also to advance our search for extraterrestrial life, somewhere in the universe beyond our solar system. For the first time, the James Webb is fully capable of analyzing the atmosphere of an exoplanet. A huge step forward, given that the composition of an exoplanet's atmosphere can give us important clues about its chances of harboring any form of life. For a planet to be potentially habitable, it needs to bring together a number of ingredients, none other than those required for the development and maintenance of life forms. On Earth, life has been able to develop thanks to liquid water, a source of energy in elements such as carbon dioxide, hydrogen, and oxygen. For an exoplanet to be habitable, it must therefore be located at a certain distance from its star, so that temperatures remain moderate and allow water to be maintained in liquid form. But it must also have the right chemical elements, a source of energy, such as volcanic activity, and an atmosphere to protect living organisms from the dangerous radiation emitted by its star. Of the more than 5,500 exoplanets discovered to date, researchers are nurturing the hope of one day finding one that meets the necessary conditions and on which a form of life could be discovered. You're about to find out how the James Webb Space Telescope can help us in this quest. To analyze the atmosphere of an exoplanet, we wait for it to pass in front of its star. This is called a transit. In this way, we can receive the light from the star that has passed through the planet's atmosphere. Thanks to this method, the James Webb's instruments will be able to identify the planet's chemical composition. The James Webb has two types of instrument: cameras to take images and spectrometers to observe light spectra. While the general public is most fascinated by the images taken by the telescope, it's the spectrometers that are of most interest to scientists. Here's how a spectrometer works. Light passes through a lens, much like a film camera. This lens concentrates all the light in a single point, so that it can then pass through a narrow slit. The light then passes through a second lens and a prism, which breaks the light down into a number of colors like a rainbow. We can then distinguish the colors that make up the light. The light spectrum is a treasure trove of information. A light spectrum is distinguished by the black lines through which molecules reveal their identity by absorbing light. This is because molecules in space will absorb certain wavelengths of light. Each molecule has its own signature. Nitrogen, hydrogen, or sodium do not have the same spectrum. By analyzing these black lines, we can identify the signature of calcium, nitrogen, or hydrogen. It's as if the molecules left their fingerprints on the light spectrum. The James Webb spectrometers have been specially designed to detect the fingerprints of molecules in the infrared part of the light spectrum. The molecules of interest in our search for extraterrestrial life are those associated with life: carbon monoxide, carbon dioxide, hydrogen, and methane. Among James Webb's notable contributions is his study of WASP-39b, an exoplanet located 700 light-years from Earth in the Virgo constellation. WASP-39b is a gas giant slightly larger than Jupiter. However, it is much less dense than Jupiter, which facilitates observations. In fact, its atmosphere is puffier and more extensive, making it easier to detect the molecules that make it up. Hubble had already studied WASP-39b and detected water vapor in its atmosphere. James Webb's more detailed instruments have enabled us to find out more. In WASP-39b's atmosphere, scientists detected a molecule essential to life: carbon dioxide, or CO2. On Earth, CO2 is produced naturally through geological processes and is vital for plant growth. James Webb also detected sulfur dioxide in WASP-39b's atmosphere, the first time this molecule has been detected on a planet outside the solar system. Once again, this discovery marks a turning point, since sulfur dioxide, present in our ozone layer, plays a crucial role in absorbing part of the sun's UV radiation, which is harmful to the Earth and to us. However, WASP-39b lacks some important elements to make it a candidate for life as we know it. Firstly, a solid surface. For this planet is a gas giant, and not, like Earth, a rocky planet. The results are still uncertain. It may have no atmosphere, but it may have a very thin one. The second missing element is a moderate temperature that would allow water to remain in liquid form. On WASP-39b, the temperature is over 870 degrees Celsius, or 1600 degrees Fahrenheit. The exoplanet is even closer to its star than Mercury is to the Sun. Although WASP-39b is clearly not habitable, the observations made by James Webb are still very useful and exciting for researchers. Above all, they provide a better understanding of the chemistry of exoplanet atmospheres. Astronomers hope to be able to establish models for the formation and evolution of exoplanets by better understanding their atmospheric evolution. In the case of WASP-39b, scientists believe it was formed by the collision of small rocky bodies, which merged to form an exoplanet. The exoplanet then moved closer to its star as it evolved. To provide such precise data, the telescope had to be calibrated over a long period of time. After its launch on December 25, 2021, the James Webb took a month to reach its L2 orbit point, located around the Lagrange point, 1.5 million kilometers, or 930,000 miles from Earth, on the opposite side of the Sun. Once in orbit, a further 5 months of calibration were required, meaning that the first images taken by the telescope were not released until July 2022. It was particularly important to ensure that the James Webb was working properly before launch. Adjustments had been made to Hubble to correct faults that were only detected after it had been put into orbit via a mission by the U.S. Space Shuttle Endeavour in 1993. But in the case of James Webb, post-launch corrections were unthinkable, given that the telescope orbits 1.5 million kilometers from Earth. Fortunately, no anomalies were reported when the telescope went into operation in early 2022. The launch performed by Ariane 5 was perfectly executed, which means the telescope still has fuel reserves for 26 years, far more than the 5 to 10 years originally hoped for. Teams monitoring the telescope are taking great care to ensure that no micrometeorites hit its mirror, or any other accident that would bring the James Webb mission to an early end. Calibration of the James Webb took several months. This step is very important to ensure the reliability of the telescope's discoveries, in particular, the age of early galaxies. If the data are not reliable, this will have an impact on the veracity of our knowledge of our universe. To calibrate the space telescope, a team used the globular cluster Messier 92 as a reference. As one of the brightest and oldest groups of stars, it has been widely observed, and a wealth of reliable data is available. This team of researchers therefore compared the data returned by the James Webb with what was already available, and adjusted the instruments and sensors accordingly. No easy task, since the James Webb has no fewer than 18 sensors, Once the calibration had been fine-tuned, the scientists were able to start measuring the brightness of distant galaxies to deduce their distance with great precision. For the moment, the most distant galaxy, the first galaxy, has yet to be identified, but researchers are not giving up hope. Thanks to this calibration, the images we can see today are not only magnificent but also realistic. Or at any rate, researchers are working to make them as faithful as possible to what the telescope observed, while adapting the images to our human eye. The images you can see, such as the phantom spiral galaxy, NGC 628, the Carina Nebula, Jupiter and Neptune with its rings, have all been reworked. The very first image taken by the James Webb left a lasting impression. It was unveiled on July 11, 2022. In this image of the deep universe, we can see the galaxy cluster SMACS 0723, made up of thousands of galaxies, and celestial objects of very low brightness. But this image was not broadcast as it was taken. It was produced by compiling images taken by the James Webb at different wavelengths over a period of 12.5 hours. The result is the sharpest infrared view of the distant universe ever obtained with a telescope. How are images taken by the James Webb reworked? The human eye can only see a very narrow part of the light spectrum, from violet to red, i.e. the colors of the rainbow. But the light spectrum is much broader than that, with light on both sides of the spectrum. The James Webb focuses on the infrared, so it can see farther than the human eye on the red side of the light spectrum. These are the data imaging developers who rework the images taken by the James Webb's near and mid-infrared instruments. In addition to computer skills, this job requires an artistic flair. It involves transposing infrared light into colors that our eyes can distinguish, i.e., one of the colors of the famous rainbow. The James Webb takes several successive images of the same celestial object with different infrared filters at different distances. The different wavelengths, i.e. near, mid, and far infrared, are then converted into the colors of the rainbow, according to the rules of data colorization, known as chromatic order. The principle is simple. Data is captured in the infrared, then shifted to the visible part of the spectrum. The principle is the same as transposing a song played on the piano into a different key. The melody remains the same. Thus, the farthest wavelength will be red, the middle wavelength green, and the closest blue. The filters are superimposed to create a colorized image. This image remains fairly flat, so it needs to be reworked one last time. It's this last stage that most calls on the developer's subjectivity and artistic sense. The idea is to obtain an image that is beautiful to look at without removing or adding elements, while remaining as faithful as possible to reality. We're now going to take a look at the latest images taken by the James Webb Telescope, which have enabled researchers to advance a little further in their quest for knowledge about our universe. Let's begin our exploration with a discovery that is one step closer to finding a habitable world beyond our solar system. On September 12, 2023, NASA reported that the James Webb had found gas showing the presence of an ocean on a planet 120 light-years from Earth, the planet K2-18b. The telescope found traces of molecules such as carbon, methane, and carbon dioxide, which could indicate that this exoplanet is covered by an ocean with a hydrogen-rich atmosphere. K2-18b would therefore be a high-oceanic planet, i.e. an ocean planet with a predominantly hydrogen atmosphere. In fact, Hubble had already found traces of water vapor in this planet's atmosphere, but the James Webb observations once again confirm scientists' suspicions. The James Webb also discovered a molecule called dimethyl sulfide, or DMS. This molecule is only produced on Earth by life, notably phytoplankton. On K2-18b, there may therefore be the equivalent of terrestrial phytoplankton. This discovery is therefore very promising and could be a clue to life on a planet in the near universe. All the more so as K2-18b is located in its star's habitable zone. NASA remains cautious and has made it clear that further checks are required to confirm the presence of an ocean on this planet. In any case, the information gathered by the James Webb is best interpreted by this hypothesis of an ocean on the planet's surface. The most widely accepted hypothesis at present is that, like Neptune, K2-18b harbors a vast high-pressure ice mantle with a surface ocean and a thinner, hydrogen-rich atmosphere. The ocean, however, would be too hot to be liquid or habitable. Confirming this hypothesis will be complicated, even with the prowess of the James Webb. Indeed, the brightness of this exoplanet's parent star is so low that when the planet transits in front of it, only a tiny fraction of the light reaches the telescope. However, just 2 observations have yielded a wealth of interesting data, and further observations are in progress. So it's a safe bet that we'll soon have new information about this planet. On the other hand, some scientists remain skeptical about the concept of a high oceanic planet. Admittedly, models and simulations show us that they could very well exist. But the existence of water in liquid form is subject to very precise parameters with very small windows, and all it takes is for one of them to move just a little for water to no longer exist in liquid form. For example, a certain level of hydrogen in the atmosphere of an exoplanet can guarantee water in liquid form on its surface, but if there's just a little too much hydrogen in the atmosphere, the water no longer exists in liquid form, but in supercritical form. Or, as on Earth, mechanisms would have to exist to stabilize the conditions that make it possible for water to exist in its liquid state. However, it is unlikely that all oceanic planets possess the same plate tectonics and volcanism mechanisms as Earth. All we can do now is wait for further data from James Webb to find out more about this exoplanet and about oceanic planets in general. Let's move on to another James Webb discovery. Take a look at this image. It was taken by the James Webb on August 31, 2023. you can see supernova 1987A, or SN 1987A, one of the best-known supernovae. Located 168,000 light-years away in the Large Magellanic Cloud, it has been observed for almost 40 years. Why, if it's already known, has this supernova been observed again with the James Webb? What did astronomers expect to discover? Quite simply, because astronomers hope to use it to understand how a supernova develops over time. To better understand James Webb's recent discoveries, let's take a look back at the story of this supernova's discovery. As its name suggests, SN 1987A was discovered in 1987, in the month of February. The discovery was made by Chilean astronomers Ian Shelton and Oscar Duhalde. It is a Type II supernova, i.e. the result of the gravitational collapse of a massive stellar core that has exhausted its nuclear fuel. Let's keep it simple. Originally, there was a star called Sandalik 69202, a blue supergiant born 10 million years ago from a stellar collision with fusion. This star had a mass 20 times that of our Sun. When the star ran out of fuel, it was unable to maintain a balance between the gravitational forces and the pressure forces generated by nuclear fusion. Eventually it exploded, releasing a large amount of light and matter into space, resulting in a Type II supernova. SN 1987A was the first supernova to be observed with the naked eye since the dawn of modern astronomy. Since its discovery, telescopes around the world have observed this supernova, including NASA's Chandra X-ray Observatory, which has examined it repeatedly during 17 years of scientific operations. Between 1999 and 2013, Chandra's data showed an expanding ring of X-ray emission that grew brighter and brighter, certainly produced by the shock wave from the supernova's explosion. Hubble had also observed this supernova, so it made sense to continue observations with James Webb. The photograph taken by the James Webb Telescope has enabled scientists to advance their understanding of this supernova. At the center of the supernova, you can see a keyhole formed by the matter ejected from the supernova, namely gas and dust. A structure that has never been observed before. To the left and right of this keyhole structure, you can also see crescents, shapes recently discovered by the James Webb. Beyond the center of the supernova, you can see an equatorial ring of material ejected tens of thousands of years before the supernova exploded. This equatorial ring contains bright hot spots that formed when the shock wave from the explosion caught up and heated the material in the ring. Around the equatorial ring, you can make out two faint outer rings, which according to researchers are the result of the interaction between the star's stellar wind emitted before the supernova and the matter previously ejected by the star. Unfortunately, the dust at the center of the supernova is so dense that not even the near-infrared light detected by the James Webb can penetrate it. That's why the keyhole is so dark in the photo. The telescope, although very advanced, was therefore unable to detect the supernova's residual star. Yet this is what scientists had hoped to observe. In fact, the collapse of a star's core, as happened with SN 1987A, usually leads to the formation of a neutron star or a black hole. In the case of this particular supernova, it would be a neutron star. Astronomers hope to be able to observe this neutron star once the gas and dust in the supernova's inner region have dissipated slightly. James Webb's next discovery we're going to talk about concerns Herbig-Haro objects, abbreviated as HH. Herbig-Haro objects are luminous regions surrounding newborn stars. When stellar winds or jets of gas spewed out by newly born stars create shock waves, and these shock waves collide at high speed with nearby gas and dust, Herbig-Haro objects are formed. On September 14, 2023, an image of the object Herbig-Haro 211, or HH211, was released. Located in the Perseus constellation, around 1,000 light-years from Earth, HH211 is a protostar that looks very much like our Sun when it was only a few tens of thousands of years old. Its mass is currently only 8% that of our Sun. HH211 had already been observed from the ground, but this is the first time we've been able to see it in such detail. The James Webb Telescope also photographed HH 797, an object located in the immediate vicinity of star cluster IC 348, at the edge of the Perseus molecular cloud, around 600 light-years from Earth. Observing this object from the ground, astronomers had noted that the cold molecular gas associated with HH 797 had a double motion. To the south, there was a redshift, meaning that the region was moving away from us. To the north, there was a blue shift, indicating that the region was moving towards us. Thanks to James Webb's observations, astronomers were able to distinguish two parallel jets instead of one, each with its own speed and history. This could mean that HH 797 is around a double star, and not, as astronomers have long assumed, a single star. Herbig-Haro objects are fascinating phenomena. The speed of the stellar winds and gas jets released by newly born stars is dizzying, and the shock waves created by the collision between these energies and the surrounding gas and dust are impressively powerful. These objects show us that within a star-forming zone, there are intense dynamics and energy flows that are both complex and incredible. With its infrared instruments like the NIRCam, the James Webb is perfectly equipped to observe newborn stars and Herbig-Haro objects, and thus better understand the dynamics at work during star formation. Let's continue our exploration of recent discoveries by the James Webb Telescope. On October 10, 2023, the James Webb observed the brightest star-forming region of the Small Magellanic Cloud, NGC 346. The Small Magellanic Cloud, also known as SMC or NGC 292, is a satellite galaxy of the Milky Way, and thus part of the local group, our group of galaxies. This irregular dwarf galaxy is visible to the naked eye in the southern constellation Toucan. It's one of the most distant objects visible to the naked eye, located some 199,000 light-years from Earth. In fact, you can only see it from the southern hemisphere, in a place far from pollution. The Small Magellanic Cloud should not be confused with the Large Magellanic Cloud, with which it forms a pair. The two are linked by the so-called Magellanic Bridge, a bridge of gas and stars. It's the Small Magellanic Cloud that interests us here, as it was in this galaxy that the James Webb was able to observe NGC 346, a particularly bright star-forming region. This image of NGC 346 was taken by James Webb's MIRI instrument. NGC 346 is a region in which stars are regularly born. It has already been photographed by Hubble, so this is not the first time it has been observed by astronomers. However, the near-infrared images taken by James Webb in January, followed by mid-infrared images in October, have enabled us to refine our knowledge of this region. The James Webb images show bands of gas and dust, dotted with luminous spots, filled with young protostars. Astronomers were astonished that the images revealed cold gas and dust emissions. The Small Magellanic Cloud is a more primitive galaxy than our own, so astronomers expected it to be fairly dust-poor. In fact, this neighboring galaxy contains fewer heavy elements than the Milky Way. Heavy elements are forged in stars by nuclear fusion and supernova explosions, so they appear late in a galaxy's lifespan. The Small Magellanic Cloud must contain heavy elements, since it is heavy elements such as silicon and oxygen that are responsible for the formation of galactic dust. The James Webb images show polycyclic aromatic hydrocarbons and dusty silicates, as well as dust heated by the most massive and brightest stars, shown in red in the photos. Bright spots and filaments can also be seen, concealing a large number of protostars. The researchers counted 1,001 red stars, most of them young stars masked by dust. The images of NGC 346 are important because they will give us a better understanding of the more primitive galaxies that existed billions of years ago, at a time called cosmic noon, when star formation was at its peak and heavy elements were present, but in lower concentrations than today. Here is an image of another star-forming region taken by the James Webb's NIRCam, which immediately struck the general public with its sharpness and detail. This is Sagittarius C, or SGR-C, a star nursery at the center of the Milky Way. This image has made an indelible impression on the general public, as well as on researchers, because until now, infrared data on this region had never been obtained with such a high level of sensitivity. Offering unprecedented detail, the image revealed many previously unobserved features of this region. According to the researchers, the center of the Milky Way is the most extreme environment in our galaxy. Sagittarius C is located very close to the center, just 300 light-years from our galaxy's supermassive black hole, Sagittarius A. This star-forming region is therefore quite far from us, at 25,000 light-years from Earth. In this image, we can see around 500,000 stars and clusters of protostars, i.e., stars in the process of forming, or if you like, baby stars, and all in a volume about 50 light-years across. One of these protostars is particularly massive, with an estimated mass 30 times that of the Sun. This protostar blocks the light behind it, so James Webb was unable to see all the stars in Sagittarius C. This is a pity, as the area hidden by the massive protostar promises to be one of the densest. The darker areas visible in the image are also star nurseries. More precisely, they are Bok globules, i.e., dark clouds of dust and gas, in which the birth of stars can begin. But what most intrigues researchers is this region, shown in cyan blue, which extends over 25 light-years and is made up of ionized hydrogen. Typically, hydrogen is ionized by energetic photons emitted by massive young stars, but in this case, it's the sheer size of the area that has astronomers wondering. On top of this, researchers are puzzled by the needle-like structures seen in the photo, which appear to be oriented chaotically in several directions. These structures are astonishing, and for the moment, astronomers have no explanation. This is the first time such structures have been observed in the heart of the Milky Way. In any case, this highly detailed image confirms that the center of our galaxy is a tumultuous zone, boiling with energy. Clouds of magnetized gas form stars, which in turn emit stellar winds, jets, and radiation that impact on the surrounding gas and create impressive objects. An extreme environment that researchers are only just beginning to study. James Webb's detailed images will undoubtedly be a great help in the quest to understand star formation at the heart of our galaxy. Among James Webb's most significant discoveries at the end of 2023 was the discovery of a never-before-seen jet stream near the equator of Jupiter. This impressive discovery was made by comparing James Webb images with those from Hubble. It was subsequently published in the renowned journal Nature on October 19, 2023. It brought to light a feature of Jupiter that had never been seen before. According to NASA, it's a high-speed jet stream, moving at around 515 kilometers per hour, or 320 miles per hour, twice as fast as a Category 5 hurricane. In fact, it's a well-known phenomenon, even though it has never been observed on Jupiter before. A jet stream is a tube of strong winds located around 8 to 15 kilometers, or 9 miles in altitude, at the boundary between the troposphere and the stratosphere. The one detected by James Webb lies above Jupiter's equator, at around 40 kilometers or 25 miles above the clouds, and extends over 4,800 kilometers or 3,000 miles across. This discovery gives us our first glimpse of how the layers of Jupiter's atmosphere interact with each other. According to the researchers behind the study, published in the journal Nature, Jupiter has a complex pattern of winds and temperatures, and the jet stream that has been spotted could vary considerably over the next 2 to 4 years. It will be further studies by the James Webb that can help us determine whether the jet's speed and altitude tend to evolve over time. On July 27, 2022, the James Webb Telescope had already delivered unprecedented images of Jupiter. These were perfectly sharp, well-defined images, revealing details of the largest planet in our solar system. The James Webb images, taken with a NIRCam near-infrared camera, reveal Jupiter's rings, its smaller satellites, Amalthea and Adrastea, and above all its polar auroras, 100 times brighter than those seen on Earth. Jupiter's polar aurorae are caused by the encounter of matter thrown up from the moon Io with the gas giant's atmosphere. A study carried out in August 2021, using recordings from the Keck Telescope in Hawaii, had shown that these aurorae acted like a radiator, providing heat to the whole planet. The James Webb images of Jupiter also show the famous red spot, which appears white because it reflects sunlight. Jupiter's Great Red Spot is a gigantic anticyclone in the planet's atmosphere, located at 22 degrees south latitude. Although it's not necessarily obvious from the James Webb images, this red spot is slightly larger than our planet itself. In 2015, its dimensions were estimated at around 15,000 kilometers, or 9,300 miles in length, and around 12,000 kilometers, or 7,500 miles in width. In the past, it would have been even larger, since it is estimated that over the course of the 20th century, it has shrunk by half. In this anticyclone, winds are said to blow at 700 kilometers per hour, or 430 miles per hour. The Great Red Spot was so named around 1878, but today it appears rather brown. James Webb did not discover this red spot, as it has been known for over 350 years, and very clear images of the phenomenon had already been obtained, notably by the Cassini-Huygens mission. However, these images will enable scientists to better study the interaction between the dynamics of Jupiter's atmosphere, chemical composition, and temperature in and above the Great Red Spot. Here are a number of images taken by James Webb and now well known to all astronomy enthusiasts. In this image, taken on July 12, 2022, you can see a young star-forming region in the Carina Nebula, 8,500 light-years from Earth. A region that had already been photographed by Hubble, but never with such precision. In this image, taken on September 12, 2022, you can see the Orion Nebula, the closest nebula to us at around 1,350 light-years from Earth. Once again, this region had already been photographed by Hubble, but James Webb's photo revealed new details. The image in front of you is very sharp. You can even make out Orion's bar, a wall of gas and dust inside the nebula, and two very bright stars that are part of the trapezium cluster. We can also see a cocoon of stars with a protoplanetary disk, conditions similar to those that led to the birth of our Sun and its planets 4.5 billion years ago. Another nebula was also photographed by James Webb on September 6, 2022, the Tarantula Nebula. Located 161,000 light-years from Earth in the dwarf-large Magellanic Cloud Galaxy, This nebula is the largest and brightest star-forming region in the entire group of galaxies not far from the Milky Way. This nebula is also home to the hottest and most massive stars known. For all these reasons, the Tarantula Nebula is of great interest to scientists. Here's a final image taken in 2022, on July 12th to be precise, by the James Webb. It shows the Southern Ring Planetary Nebula, located around 2,500 light-years from Earth, in the constellation of the Veils. James Webb's image enabled scientists to discover the origin of this planetary nebula, a binary system of dying stars. On October 30th, 2023, the James Webb unveiled a new nebula image, the Crab Nebula. Located 6,500 light-years away in the constellation Taurus, this nebula is in fact a supernova remnant. The Crab Nebula had already been photographed by Hubble in 2005, but here again, the details provided by the James Webb images have enabled scientists to better understand its origin. The James Webb data have enabled us to establish the composition of the ejected material, in particular, its iron and nickel content, which will tell us what type of explosion produced the Crab Nebula. By the way, take a look at the two images side by side, the Hubble image and the James Webb image. You can see that in the James Webb image, there's more detail in the central regions of the nebula, where you can see the emission of dust grains. The orange filaments you can see in the image taken by the James Webb are the remains of a star that has now disappeared. The supernova created by the explosion of this star was seen on the Asian continent in 1054. For 23 days, the supernova shone brightly and could even be seen in broad daylight. Even today, the nebula continues to expand at a speed of 1,500 kilometers per second, or 930 miles per hour, as a result of this explosion. In the center of the image, you can see a translucent zone of what is known as synchrotron radiation. Synchrotron radiation is generated by the presence of a pulsar, a neutron star that rotates very rapidly and emits strong radiation. Thanks to these breathtaking details, scientists hope to glean valuable information for a better understanding of a star's life cycle. The image before your eyes is considered one of the most complete views of the universe ever obtained. This image has been reconstructed using James Webb and Hubble images. It shows the MAX 0416 galaxy cluster, 4.3 billion light-years away. More precisely, MAX 0416 is a pair of colliding galaxy clusters which will eventually merge to form an even larger cluster. Researchers combined images taken in visible light by the Hubble telescope and in infrared by the James Webb Telescope to reconstruct this colorful view of our universe. In fact, why is this image so colorful? Quite simply, because it shows thousands of galaxies that appear differently colored according to the wavelength range in which they shine, i.e., from 0.4 to 5 microns. The nearest galaxies, regions of intense star formation, appear in blue and were detected by Hubble. The most distant galaxies, on the other hand, appear in red and were detected by James Webb, as they are too far away for Hubble to see. Objects colored green are located at mid-distance. James Webb didn't just take a picture of this cluster of galaxies at a given moment in time. He observed the region 4 times, a week apart, to identify what are known as transient objects. Transients are objects whose brightness varies over time. 14 transient objects were detected, 12 of which are likely to be single stars or multiple star systems, and 2 are likely to be supernovae. This means that transient phenomena could be much more numerous than previously thought. Among the transient phenomena identified in the MACS 0416 cluster, one in particular has caught the attention of scientists. This is a giant star that has been nicknamed Mothra because of its monstrous nature. It is located in a galaxy that existed some 3 billion years after the Big Bang and is amplified by a factor of at least 4,000 through gravitational lensing. Mothra was already visible in Hubble's observations almost 10 years ago, which is quite unusual. Indeed, it would take a very specific alignment between the galaxy cluster in the foreground and this star in the background for it to be so amplified. However, the mutual movements of the star and the cluster should have broken this alignment. The explanation put forward by the scientists is the presence of an additional object in the foreground group, which would add magnification, like a globular cluster. This object would have a mass between 10,000 and 1 million times that of our Sun. The MACS 0416 cluster has been nicknamed the Christmas tree cluster because, according to NASA researchers, it is very colorful with flickering lights, like the lights on the tinsel of a Christmas tree. Among the most recent images taken by the James Webb is this impressive photograph. This is no trick. This cosmic ghostly figure is a galaxy in formation called Aztec 71, more precisely, a dusty star-forming galaxy. This is a type of galaxy hitherto reputed to be very rare and almost invisible. Hubble had already attempted to photograph this galaxy in formation, but without any real success. Aztec 71 is very difficult to observe. This galaxy is the seat of star formation, but it's shrouded in a dusty veil that's very difficult to penetrate. That's why Hubble, which couldn't see in the infrared like James Webb, wasn't able to obtain satisfactory images. James Webb's image, broadcast on October 10, 2023, is very striking. It looks like a ghostly face. It looks like a tiny drop in the vastness of the universe. But this galaxy is actually forming hundreds of new stars every year. This discovery shows us that there could be a whole population of galaxies hiding from us that we won't be able to observe until we develop even more powerful instruments than the James Webb, capable of seeing in even more extreme wavelengths. This discovery has also led researchers to claim that this type of galaxy, thought to be extremely rare, is in fact 3 to 10 times more common than previously thought. Like the image you've just seen, this photo of the exoplanet WASP 107b, taken by the James Webb, is also very impressive. WASP 107b is a gas giant, orbiting a highly active K-type main sequence star, located around 200 light-years from Earth. It is nicknamed the Hot Super Neptune. One of its special features is that it is one of the exoplanets with the lowest known density. Its mass is only 12% that of Jupiter, while its diameter is comparable. This is due to the fact that its atmosphere is greatly expanded by the radioactive heating of its star, around which it orbits in just 6 days. Temperatures in its atmosphere reach hundreds of degrees. WASP 107b's highly expanded atmosphere has earned it the nickname of Cotton Candy Planet. In any case, it facilitates measurements of the planet's atmospheric spectrum. Astronomers had already discovered helium in its atmosphere thanks to Hubble's observations. Observations by the James Webb have taught us new things about this cotton candy exoplanet. The data provided by the telescope was analyzed by a team of European astronomers, co-led by researchers from CEA and the Institute of Astronomy at the Belgian University KU Leuven. The scientists were able to detect silicate clouds in WASP 107b's atmosphere, a first for a planet of this type. According to their analysis, WASP 107b's atmosphere contains not only clouds of silicate particles, cousins of sand grains, but also molecules of water vapor and sulfur dioxide SO2. Surprisingly, however, no traces of methane were found. This remains unexplained for the moment, unlike other discoveries such as sulfur dioxide, which have been elucidated by new models. Astrophysicists still don't understand why no trace of methane has been detected in the atmosphere of WASP 107b, which might force them to revise the models of exoplanet atmospheres known to date. Nevertheless, if the discovery of silicate clouds initially surprised scientists, it can be explained. What astonished astronomers was the presence of these clouds at high altitude. The temperature is only 500 degrees Celsius or 930 degrees Fahrenheit at this altitude, yet the melting temperature of silicate particles tells us that they should form deeper in the atmosphere at higher temperatures. Surprisingly, sand clouds exist and persist at high altitudes. In fact, it would seem that the phenomenon is roughly similar to that of the water cycle on Earth, except that rain is not made up of drops of water but of sand. The droplets of sand rain evaporate into deeper, hotter layers, and the resulting silicate vapor is then carried upwards, where it recondenses to form silicate clouds once again. A discovery that overturns our understanding of exoplanet atmospheres. WASP 107b appears to be an exotic world, completely different from our own, with complex chemical interactions. There is no equivalent of this exotic world in our solar system, and that's what's so fascinating. Here's another image that may not mean much to you, but represents a real breakthrough for astrophysicists. This image is none other than the discovery by the James Webb Telescope of the most distant black hole ever detected in X-rays. This discovery was made possible by the combination of two space telescopes, the James Webb and Chandra. Because it emits X-rays, we know that it is a supermassive black hole in full growth. The study of this black hole will be invaluable in understanding how some of the first supermassive black holes in our universe were formed. Most astrophysicists agree that there are compact stars at the heart of the vast majority of large galaxies, containing at least 1 million and sometimes several billion solar masses, and behaving as predicted by black hole theory. In other words, supermassive black holes. What we don't know is how these supermassive black holes came to be. There are a number of theories. One of the most widely accepted is that black holes are formed by the accretion of matter from cold filaments. What are cold filaments? They are filaments of cold gas, channeled by filaments of dark matter, which are thought to feed the star-forming matter that makes galaxies grow. Many other hypotheses have been considered. The existence of primordial stars of very high mass, the existence of giant black holes produced during the Big Bang. The discoveries of the James Webb Telescope should enable us to find out more. Let's return to our image. First, Chandra, a space telescope in orbit since 1999, detected a source of X-rays in the UHZ1 galaxy, in the direction of the Able 2744 or Pandora cluster of galaxies, 3.5 billion light-years from the Milky Way. The Pandora cluster, thought to have resulted from the merger of 4 smaller galaxy clusters, is particularly rich in dark matter. This creates a useful gravitational lensing effect for astronomers, making it easier to observe distant galaxies in the visible or near-infrared range. From the data collected by James Webb, researchers were able to establish that galaxy UHZ1 is seen as it was only 470 million years after the Big Bang. As for the Chandra data, they show that the X-ray source associated with this galaxy has all the characteristics of a growing supermassive black hole. This would make it the most distant black hole ever observed in X-rays. What's more, this black hole would have unusual characteristics. With a mass 10 to 100 million times that of the Sun, it contains a quantity of matter equivalent to that of all the stars in the galaxy where it lived in a past revealed to us by photons that traveled more than 13 billion years. We are therefore observing a black hole at an extremely early stage, with a mass similar to that of its host galaxy. According to the researchers, this is a very brief phase in the life of a black hole, during which it weighs about as much as the stars in its galaxy, before falling behind. All these observations confirm the hypothesis that supermassive black holes are the result of a gravitational collapse of a very large gas cloud. Since its launch at the end of 2021, the James Webb Telescope has enabled numerous advances in the fields of cosmology and astrophysics. Not only have new cosmic objects been discovered, but even more knowledge has been gained about the objects already photographed by Hubble, with captivating, colorful images packed with detail. The discoveries made by the James Webb have provided new insights that will not only help us better understand certain cosmic phenomena, but also advance our understanding of the phenomena at the origin of our universe. Here's a first example. In a study published on November 8, 2023, in the journal Astrophysical Journal Letters, a team of researchers explained the role of protoplanetary disks in planet formation, deduced from observations of the James Webb. Protoplanetary disks are agglomerations of gas and dust. They are home to icy rocks, which release water vapors under the effect of extreme temperatures. Protoplanetary disks are therefore predominantly composed of cold water. As they approach newborn stars, icy rocks evaporate, forming rocky planets. This phenomenon was certainly behind the creation of our solar system some 4.6 billion years ago. This hypothesis suggests that even in the most extreme environments of our galaxy, where protoplanetary disks are found, telluric planets like our own could form, which considerably widens the field of possibilities. Here's a second example of a discovery made thanks to the James Webb that has profoundly changed the theories of modern astrophysics. In the vicinity of the Big Dipper constellation, the James Webb Telescope has captured some very old galaxies that, according to our current theories, shouldn't even exist. The 6 galaxies discovered by the James Webb are estimated to have formed only 500 to 7 million years after the Big Bang. They are therefore almost 13 billion years old. However, according to the researchers' calculations, they could contain as many stars as the Milky Way, which doesn't fit our current models. According to currently accepted theories, there must not have been enough matter at that time for galaxies to form as many stars as the Milky Way. These discoveries call into question the very principle of the formation of the first galaxies. At first, because James Webb had already observed very old galaxies, formed around 350 million years after the Big Bang, but they were small and didn't contain as many stars. Galaxies that are both very old and massive, never before seen. It's possible that the red dots observed by the researchers are not very old galaxies, but quasars or supermassive black holes. Or they could be smaller galaxies than scientists have calculated. New data will be needed to confirm the discoveries and find out whether or not we need to revise our current theories and models. New data, that's what we're waiting for to complete all the somewhat disturbing discoveries made over the last 2 years by the telescope. Scientists are keen to make the most of James Webb's potential and use its mission to confirm and refute each of these strange discoveries. Above all, these observations are expected to enable us to reconstruct the history of the universe without any blanks. In fact, the ultimate goal is to fill in all the gaps in our understanding of the universe. How did the universe ignite? How did galaxies come into being? At present, we still don't know how to go back to the first instance of the universe. It's as if we had photos of the universe as a baby, arriving home from the maternity ward, but not of its very first moments. The very first memory we have of the birth of the universe is when it is 378,000 years old. The universe is then what we call the cosmic microwave background. It's made up of tiny specks, representing variations in density. The densest regions become galaxies and stars until they reach us. But how did these tiny specks create galaxies and stars? This period, which lasted several 100 million years when stars didn't yet exist, is known as the Dark Age of the universe. The universe was made up mainly of hydrogen, like a fog in the end, since hydrogen atoms reflect light radiation and we can't see through them. Our knowledge of the history of the universe lacks that moment when the universe emerges from the Dark Ages and the first stars and galaxies begin to take shape. This is what we'd like to understand with James Webb and future generations of telescopes. Whether in literature or more recently in film, there are many stories, more or less bloody, recounting the adventures of evil blood-drinking creatures, vampires. These legendary monsters have been described in many ways across the ages and continents. Dracula, the famous character born from the pen of Irish novelist Bram Stoker, is still part of the imagination. However, the quest for eternal life that these fanged monsters covet has found an echo in the cosmos. Some stars, despite the laws of astrophysics, seem to have found a way to offer themselves a second life, if not eternal existence. These are the so-called vampire stars, better known as blue stragglers. These vampire stars, found mainly in globular clusters, shouldn't exist. At the very least, they should have the appearance of their many neighbors, old stars that have lost their luminosity, namely red giants. But it turns out that these blue stragglers, unlike many of the surrounding stars, are blue, hot, and massive. How is this possible? Could they be stars from the galactic disk that have migrated through a gravitational interaction mechanism towards a globular cluster? Or could it be that these stars have fallen behind their fellow stars, as if they had found their elixir of youth? That's what we'll try to elucidate in this video. But you probably already have an idea of what we'll be observing over the next few minutes. If you haven't, the names of these strange stars should provide you with a sufficiently eloquent clue. Before we start making comparisons, I suggest we take a closer look at the life cycle of an ordinary star. The first stage in a star's life is its birth, or more precisely, its formation. This occurs when a cloud of gas and dust, in other words, stellar matter, collapses in on itself. Of course, depending on the primary composition and mass of this cloud, the star in the making will evolve in different ways. Some will never go beyond the brown dwarf stage, while others, benefiting from abundant raw materials, will go so far as to create a black hole after a very long process and complete collapse. During the very first phase of transition, which can last several thousand years, the fall of gas towards the center of the cloud, due to gravitational energy, heats up the star in the process of formation. The pressure produced by the heat slows the contraction, and the star glows like a glowing ember. On the other hand, if the star's mass is less than 8% of the Sun's, its hydrogen cannot fuse. However, the heavy hydrogen present in the universe allows this brown dwarf star to shine minimally among its contemporaries. The next passage begins the main sequence of a star's life cycle, a crucial and relatively stable stage in its existence. The duration of this phase depends greatly on the type and size of the star concerned. The main sequence represents the period during which the star shines by converting hydrogen into helium in its core through the process of nuclear fusion. This process depends on the star's size, mass, and composition, but on average occurs when the star's core reaches a crucial temperature of around 10 million degrees Celsius, or 18 million degrees Fahrenheit. At these extreme temperatures, nuclear reactions become energetic enough to fuse hydrogen nuclei, producing helium while releasing a large amount of energy. This energy radiates outwards, creating a pressure that counteracts the gravitational force, trying to make the star contract in on itself. The time a star spends on the main sequence depends on its mass and hydrogen consumption. Massive stars with more available hydrogen will consume their fuel more quickly. For example, our Sun, a G-type star, has been on its main sequence for around 4.6 billion years, and is expected to remain there for another 5 billion years or so. By comparison, a smaller, less hot M-type star could remain on the main sequence for tens or even hundreds of billions of years. Larger, hotter O-type stars will burn through their hydrogen much faster, remaining on the main sequence for only a few million years. Once the hydrogen in the star's core is exhausted, the star leaves the main sequence, inaugurating the next phase of its evolution, which could be that of a red giant or supergiant, again, depending on its initial mass. Throughout the cosmic ages, a star passes through several distinct phases, each determined by the delicate balance between gravity and thermal pressure, as well as by the amount of hydrogen available for nuclear fusion. From the very first moments of its birth, the star begins its life by transforming hydrogen into helium in the heart of its fiery entrails. However, this reserve of hydrogen is not eternal. As the hydrogen is depleted, the star enters a period of transition. During this phase, gravity begins to take over, further compressing the star's core, which in turn raises its temperature. This rise in temperature triggers the fusion of helium into heavier elements, such as carbon, while at the same time causing the star's surface to expand and cool. From there, the star's future is shaped differently, according to its original mass. Red dwarfs, tiny stars with less than half the mass of the Sun, live extremely frugal lives. Their surface temperature remains relatively low, around 3,300 degrees Celsius, and their frugal composition of hydrogen enables them to shine continuously for trillions of years. At the end of this prolonged period, these modest, persevering stars eventually transform into white dwarfs. Then over time, cool and solidify into crystalline spheres of carbon and oxygen. Stars similar to our Sun, with masses between 0.5 and 8 times the solar mass, have a more turbulent life. After exhausting their hydrogen, their cores contract, and the temperature rises drastically, reaching up to 100 million degrees Celsius, or 180 million degrees Fahrenheit. This intense heating initiates the fusion of helium into carbon. They then swell into red giants, colossal entities up to 1,000 times the diameter of the Sun. After ejecting their outer layers in the form of planetary nebulae, they leave behind a hot core that gradually cools to form a white dwarf. Slightly more massive stars, between 1.5 and 8 solar masses, follow varied trajectories, oscillating between cycles of contraction and expansion, fusing heavier and heavier elements in their cores until they reach iron. These complex thermodynamic processes lead to Type II supernovae, from which they may leave behind neutron stars or black holes. For stars whose mass exceeds 10 times that of the Sun, their destiny is often to become blue giants. These massive celestial entities are distinguished not only by their impressive size, but also by their frantic energy consumption. Their great mass means that they burn their nuclear fuel at a frenetic pace, resulting in a relatively ephemeral existence on the cosmic scale, lasting only a few million to a few tens of millions of years. During the blue giant phase, these stars undergo significant transformations. They leave the main sequence after exhausting the hydrogen in their cores, triggering a series of nuclear reactions that convert helium into carbon, and successively heavier elements are formed through nuclear fusion processes. The star continues to expand, its core contracting as its outer layers move away from the center. The ultimate fate of a blue giant is just as spectacular as its life. As nuclear fusion continues, generating heavier and heavier elements, the star's core becomes heavier until it can no longer support its own gravity. At this crucial stage, a cataclysmic implosion occurs, leading to one of the most fascinating phenomena in the universe, a supernova. This stellar explosion releases astronomical energy, briefly illuminating the cosmos before slowly fading away. The remains of these blue giants can then either form a dense neutron star or, if the mass is sufficient, a black hole. If blue giant stars are anything like vampire stars, the presence of the latter in globular clusters, where the star population is very old, raises a question, and it has something to do with the lifespan of blue giants. After all, blue giants are not known for living long. Blue giants, as their name suggests, are among the largest stars we can observe. Their blue color also means that they are the hottest of all observable stars, the others reflecting white, yellow, or even red light when they are at the end of their life, as we've just seen. The high luminosity and extremely hot temperature of these stars is due to the fact that they burn up their resources rapidly without restraint. This means that these stars run out of fuel very early on. For this reason, blue giants have the shortest lifespan of all stars, between 10 and 100 million years, making them quite rare. For the same reason, blue giants mainly reside not far from the star-forming regions where they were born. Among the best-known blue stars are Regulus, the flagship star of the Leo constellation, Spica, and Rigel, the brightest stars in the Virgo and Orion constellations. But the most massive star ever observed is R136A1, located 163,000 light-years from Earth, in the Tarantula Nebula. It is at least 265 times more massive than our Sun. R136A1 is an extraordinary star. Initially considered a blue supergiant, it is now classified as a Wolf-Rayet type, WN5H star. In the early stages of its existence as a blue supergiant, R136A1 was characterized by extremely high temperatures and intense luminosity, all wrapped up in a spectacular bluish hue. These massive stars undergo intense nuclear reactions, fusing hydrogen into helium at an accelerated rate. Over time, the substantial loss of mass due to powerful stellar winds and the reduction in available nuclear fuel lead these majestic stars to transition to the Wolf-Rayet stage. Wolf-Rayet stars, like R136A1, display even more powerful and rapid winds, eroding their outer envelopes and exposing their fiery, tumultuous cores, where heavier elements are currently being formed. These stellar winds help seed the universe with a rich diversity of elements, serving as building blocks for future generations of stars, planets, and eventually life. A question is probably emerging in your mind. How can blue stars be found in globular clusters, which, far from being able to produce young stars, are populated exclusively by old red stars? However, blue stars do exist in this type of calm environment, at least on the surface. These are known as blue stragglers. These blue stars, which have all the characteristics of young stars during their main sequence, nevertheless evolve, mainly in globular clusters, which are conglomerates of very old stars. Indeed, these clusters, which gravitate in the galactic halo, were probably formed at the same time as their host galaxy, several billion years ago. So how can they be home to blue stars, the oldest of which are only 100 million years old? Are these juvenile-looking stars, located mainly in the center of clusters that sometimes contain hundreds of thousands or even millions of stars, really as young as they seem? Or have they found a subterfuge to extend their lifespan? And if so, to what detriment? That's what we're going to try to elucidate through the various discoveries made about them. The discovery of blue stragglers is a very recent one. It dates back only to 1953. Alan Sandage, an astronomer at the Carnegie Observatories in Pasadena, California, first described this type of star while observing M3, a globular cluster located some 33,300 light-years from Earth in the Hound constellation. While studying this star cluster, which is one of the largest and brightest globular clusters on record at the time, he was surprised to discover it. While carrying out photometry, he noticed in the midst of countless old stars and several dozen variable stars, the presence of an atypical type of star, bright blue and hot. Unlike most of the other stars in the observed cluster, which seem to have a common past and thus to have formed at the same time, the stars discovered left him perplexed. Indeed, the stars in question had all the characteristics of a newly formed star, something that seemed more than unlikely within this globular cluster, whose age is estimated at over 11 billion years. However, these blue stars, which defy the rule of the Hertzsprung-Russell diagram, do exist. This diagram, used to study stellar populations, is in fact a graph showing the luminosity of a set of stars as a function of their effective temperature. But Alan Sandage's recently discovered star type is an exception to the rule, as it doesn't fit neatly into this spectral classification. Indeed, a blue straggler, which is a massive main sequence star, should theoretically not exist in this globular cluster. The scientific community therefore set out to elucidate what it considered to be the equivalent of an anomaly. When and how did such a massive star, 2 to 3 times the mass of the other main sequence stars in its host globular cluster, come into being? As more and more similar stars came to light, several theories began to emerge. The most obvious of these was that the existence of such a star was potentially linked to its period of formation. The latter must have been much more recent than the formation of the cluster population as a whole. However, this explanation failed to convince most astronomers. In fact, these late-forming stars needed large quantities of dust and gas to form. However, the cluster got rid of these residual elements a long time ago, during its formation. The second hypothesis was that this star must be foreign to the cluster in which it was detected. Although spotted in the field of observation of the cluster under study, it might be physically unrelated to it and located on a different plane. In the same vein, another idea has also been put forward. The star may have been torn from the galaxy's disk and captured by the star cluster when it was a little too close to it. These last two theories were not accepted for very long, not least because of the location of these atypical stars within their host globular cluster. Indeed, blue stragglers are essentially located in the most central regions of the stellar cluster that hosts them, implying that their physical integration into the structure has not occurred recently. This possibility is inconsistent with their recent formation. A final theory, dating back to 1964, was based on possible interactions within the existing group of stars. Astronomers Fred Hoyle and W.H. McCrae put forward an identical hypothesis, namely that two neighboring stellar mass stars, forming a tight binary system, would have collided or transformed matter and eventually merged, giving rise to this massive, luminous colossus. For several decades, the mystery remained unsolved. Intrigued, many astronomers have continued to study these most massive and ancient groupings of stars in the universe, in search of answers about the formation and evolution of the Milky Way, and indeed of the universe. The 47 Tucanae cluster, one of the largest in our galaxy, is one of the most closely observed star clusters. Located in the Tucan constellation, around 15,000 light-years from Earth, it is a relatively compact globular cluster, with an estimated diameter of 140 light-years. In 1991, aided by the Hubble Space Telescope, itself equipped with a high spatial resolution, ultraviolet-sensitive camera, a team of astronomers discovered the presence of several blue stragglers at the heart of the cluster. In their statement, the scientists revealed that they had resolved 21 of them, which they believed to be extraordinarily concentrated in the center. Their location seems to support the hypothesis that these stars are created by collisions, mergers, or close encounters between stars. The fact that they are located within the cluster itself, in its densest and most luminous part, also explains why these massive stars have remained invisible for so long. Indeed, Only instruments employing high spatial resolution, coupled with ultraviolet sensitivity, are able to study the compact core of 47 Tucanae and many other groups of stars in greater detail. The use of this new technology has thus opened the door to abundant discoveries. Whereas ground-based images yielded only a few dozen stars in a precise area of the cluster studied, this onboard camera will have enabled the resolution of around 600 stars. Comparing the images obtained by these two techniques enabled astronomers to discover 21 stars that are extraordinarily bright in ultraviolet light. By comparing the luminosity and temperature of these particularly bright stars with a computer model predicting how main sequence stars appear in ultraviolet wavelengths, the scientists concluded that they were indeed blue stragglers. What's more, the high concentration of these specific stars towards the cluster's core suggests that they are relatively much more massive than the vast majority of its component stars. The high mass of some of these stars could also be explained by the presence of binary systems. A considerable population of millisecond pulsars and binary stars has also been discovered in 47 Tucanae, supporting the idea that close gravitational encounters between single stars, binary stars, and even binary systems could well take place in this zone. A few years later, in 1995, another group of astronomers focused on one of these blue stragglers. Still using the Hubble telescope, they were able to observe its behavior. The result, which they describe as exciting, will help to support a number of existing theories on the formation and evolution of these enigmatic stars. After analyzing the star's spectrum and measuring its temperature, radius, and rotation speed, they were able to obtain the star's mass. While its derived temperature and mass are consistent with the specifics of a normal star with a mass around 1.7 times that of the Sun, its speed is unexpected. In fact, it turns out that this blue star rotates 2 to 3 times faster than its counterparts, and 75 times faster than our Sun. All these elements offer scientists the opportunity to understand how blue stragglers are formed. While it is becoming clear that a star of this type is created by the fusion of two low-mass stars, it remains to be seen by what process. Was it a violent collision, or a long process of fusion between binary stars, with one siphoning energy from the other? According to the scientists, this second hypothesis produces rapid orbital movements of the binary star, generating, in effect, an accelerated rotation of the pair in the final phase of fusion. Over the years, thanks to cutting-edge technology, more and more blue stragglers have been detected. In a 2006 study, which examined the chemical signatures of 43 of the blue stragglers in cluster 47 Tucanae, 6 of them had lower concentrations of carbon and oxygen than their counterparts. The scientists concluded that their surface material must almost certainly have been literally sucked up from the deep interior of a parent star in a double system. The same researchers also studied these atypical stars in 56 other globular clusters. They found that the amount of blue stragglers in a particular cluster was unrelated to the potential collision rate. Thus, they partly put to rest the theory that these stars were the result of collisions between several stars. Instead, there did seem to be a correlation between blue stragglers and the rate of binary stars in these different globular clusters. This finding enabled them to prove that the majority of blue stragglers, including those closest to the core of these clusters, are indeed the descendants of two binary stars. It took more than 50 years for astronomers to unravel the mystery of these immature-looking yet ancient stars. Among the many stars studied in an attempt to better understand these curious objects, one has caught astronomers' attention for its strange behavior. This is the star SS Leporis, also known as 17 Leporis. Long catalogued as a variable star in the Hare constellation, SS Leporis is in fact a rather unusual binary star system. The two stars revolve around each other in 260 days, and the distance between them is only slightly greater than that between the Earth and the Sun. The largest and coldest of the two stars, a red giant, spans a quarter of this distance. To give you an idea of their proximity, the orbit with its companion could be compared to that of Mercury with the Sun. But above all, this red giant, which is in fact the more evolved of the two, paradoxically happens to be the less massive of the two stars. How could these mass ratios be reversed in such a way? To unravel the mystery of this unusual phenomenon, scientists decided to study the dynamics of the system while observing the most central parts, inaccessible with conventional telescopes. In 2010, astronomers created a virtual telescope 130 meters in diameter, offering a view 50 times sharper than that provided by NASA's Hubble Space Telescope. To achieve this, they combined light captured by 4 telescopes at the European Southern Observatory's Piranal Observatory. While the scientists were convinced that matter was transiting from one star to another in this unusual system, they didn't know how. Their discovery has enabled them to assert that this mass transfer does not follow similar patterns already known. The new, extremely precise observations showed that the red giant is smaller than they had previously thought. Its companion, a blue star, although smaller in size, turns out to be the hotter of the two. Its mass is around 2.7 times that of the Sun, compared with 1.3 times for the red giant. The process by which this star flows matter onto its companion star proves far less easy to explain, especially as no flow of matter is visualized between the two stars. Researchers are beginning to put forward the idea that the blue star, with its highly superior mass, has been vampirizing its imposing neighbor for almost 500,000 years. The notion of a vampire star which feasts long and insidiously on a neighboring star became obvious. The vampire star seems to be sucking not the blood, but the hydrogen and plasma from its neighbor, who thus becomes a victim with a shortened lifespan. Unlike cannibal stars, vampire stars, better known under the scientific term of symbiotic binaries, do not quickly devour their prey. The first cannibal star was studied by the European Space Agency in 2004. Researchers had the opportunity to observe a fast-rotating star. It is a super-dense neutron star just 20 kilometers across, initially 8 times more massive than our Sun. Although its mass is astronomical, a thimble's worth of its material, weighing close to 1 billion tons, its small size has meant that it has been virtually invisible to observational instruments. However, on December 2, 2004, it emitted a sudden and powerful X-ray eruption, revealing itself to Integral, the European Space Agency's International Gamma Ray Astrophysics Laboratory, and NASA's Rossi X-ray Timing Explorer spacecraft. The measurements confirmed that this was one of the fastest spinning pulsars ever studied, with a dizzying speed of 600 rotations per second, which is gradually accelerating. This frenetic rotation is the result of the absorption of gas extracted from a companion star. When this gas crashes onto the star's surface, it causes it to heat up to a temperature of almost 1 billion degrees, releasing extraordinary quantities of X-rays and gamma rays. In short, it makes short work of its neighboring star, which shrinks irreplaceably. This is why this cannibal star is nicknamed the Black Widow. Even more unusual, in 2015, a NASA telescope caught a cannibal star in the middle of a feast. This is a white dwarf at the end of its life, whose gravity is so powerful that it is capable of attracting and eventually disintegrating a nearby telluric planet. In 2011, still intrigued by this unexplained phenomenon, scientists also turned their attention to the open cluster NGC 188. Located in the Cepheus constellation, 6,680 light-years from our solar system, this cluster features 21 blue stragglers, most of whose stars are over 7 billion years old. Detailed observational data from the Webb Telescope at the Kitt Peak Observatory in Tucson, Arizona, were used to analyze and compare the 3 main theories concerning the formation of blue stragglers: star collisions, star mergers, or mass transfer from one star to another. Collisions or mergers would be conceivable if the companion stars appeared more massive, which is not the case. The mass of these companions, whose luminosity remains low, can only be determined by observing the blue stragglers. These are subject to a gravitational force from the red giants, creating an oscillation during their orbit. By observing the movements of the blue stragglers, they were able to determine that 16 of them must have a much more discrete companion. The data collected enabled the researchers to assert that each companion star had a mass about half that of the Sun, corresponding to a white dwarf. But what better way to confirm their assertions than with an image? However, in 2011, the technical means available are not yet sufficient to observe this type of star, whose luminosity is relatively low, especially as it lies close to a sparkling blue straggler. Using ultraviolet wavelengths, a team in 2015 was able to prove that 7 of the 21 blue stragglers had a white dwarf as a companion, thus supporting the 2011 conclusions of their colleagues. In her study, she points out that only white dwarfs formed within the last 250 million years can be detected, the others being too cool to be detected and thus confirmed. Among the other blue stragglers, 7 showed evidence of mass transfer between stars by other means. All in all, it proves that a quarter of the oldest stars do not evolve into red giants, but turn into blue stragglers with surprising luminosity and strange behavior. We now know how blue stragglers are formed.
Stars that appear bright and fresh alongside many faded stars in ancient clusters. They give themselves a new lease on life by absorbing matter from their companion stars. These are not stars that have migrated or collided, giving rise to a massive bright new star. It's a case of one star vampirizing another, giving itself a second life. Vampire stars are mainly observed in stellar clusters. These groups of stars, which formed more or less at the same time as their host galaxy, are home to the oldest stars. Almost exclusively populated by red giants, they nevertheless shine brightly in our starry skies due to their high concentration. Millions of stars are crammed into an area that in other parts of the galaxy might contain only one star or even none at all. In these spherical clusters, some stars appear far less advanced than the majority. But if these younger-looking stars were the result of collisions and mergers, they would have to show age differences. However, the study of these blue stragglers within the same cluster has shown that they all formed at roughly the same time. They are therefore not the result of collisions due to random displacements. Since 2011, scientists have known that they are the result of mass transfer between two very specific stars. Let's take a closer look at the process by which these stars manage to rejuvenate themselves. When two stars form a binary system, orbiting each other, they evolve according to the same pattern. As the two stars age, they gradually evolve into red giants. In the process, their volume increases steadily, until they reach several hundred times their initial size. As they move ever closer together, the distance between them shrinks considerably. Gravitational interactions become increasingly important. Inevitably, the star with the highest mass outweighs its companion star. As its gravitational force is greater, it will gradually absorb the outermost layers of gas, which are only weakly held back by the gravity of the second star at the end of its life. Mass is inexorably transferred from the cooling red star to the star that is gradually regaining its youth. By stirring up the hydrogen fuel, the latter generates nuclear fusion at a faster rate. The hydrogen burns hotter and bluer. The least massive, which ends up completely stripped, retains only its core. It loses its red giant status and becomes an insignificant white dwarf. Meanwhile, the vampire star gains extraordinary mass, and after its rejuvenation, begins to shine brightly. At first glance, she may appear youthful, but her real age is much more advanced, just like those who undergo facelifts. While the mystery surrounding the formation of vampire stars seems to have been solved, studies of them are still going strong. The stars contained in the clusters of each galaxy have yet to reveal all their secrets. All the more so, as these stars are the ancient witnesses of many cosmic formations. But we still have to get them to talk. Eager to learn more about their past, Canadian students from the Department of Physics and Astronomy at the University of British Columbia published a study in 2016. It focused on the formation and evolution of blue stragglers in the 47 Tucanae cluster. Knowing that all the stars in the same cluster are at the same distance from the observation site, i.e. the Earth, it becomes easier to compare their apparent magnitude. The students created a color magnitude diagram, which is simply the observational version of the Hertzsprung-Russell diagram. they were able to observe the population of blue stragglers in this cluster. Their findings suggest that the existence of these stars, which are too blue in this aged environment, is the result of a number of mechanisms, as well as being dependent on the environment in which they evolve. They began by separating the stars into different populations. In equal numbers, bright blue stragglers and faint blue stragglers, main sequence stars, binary main sequence stars, and red giants. In a second step, the researchers estimated the cumulative distribution of each of these categories along the cluster radius of their diagram. They found that bright blue stragglers are more concentrated in the inner regions, while fainter blue stragglers are much more prevalent in the peripheral zone. What's more, the cumulative radial distribution of bright blue stragglers is not echoed by other populations, making it difficult to link their formation to a specific group of stars. On the other hand, faint blue stragglers and main sequence stars show a very similar distribution, suggesting that a binary system may indeed be at the origin of these atypical stars. In short, the study demonstrated that different mechanisms could lead to the formation of blue stragglers. Interactions between several systems seem to dominate in the central regions, resulting in more massive and luminous objects, while binary evolutions appear to be the most common scenario in the periphery of these clusters, generating fainter blue stragglers. They were also able to conclude that the evolution of blue stragglers at equal mass is similar to that of main sequence stars. While these findings still need to be confirmed by future observations, they nevertheless allow us to learn ever more about these strange and surprising blue stragglers. Again, thanks to the Hubble Space Telescope, 26,000 light-years from our Sun, blue stragglers have been detected this time, not in a cluster, but in the bulge of the Milky Way, i.e., at the very heart of the galaxy. In this congested area, which corresponds to the former hub of our Milky Way, amid countless aging stars, blue stragglers also reside. In 2006, a 7-day survey was carried out. Called Sagittarius Window Eclipsing Extrasolar Planet Search, its aim was to detect hot Jupiter-like planets orbiting very close to their stars. After observing and collecting information on the variability of 180,000 stars in the extremely populated central bulge of our galaxy, the scientists were able to determine that most of them were aging Sun-like stars and cooler red dwarfs. In an area once populated by giant blue stars that exploded as supernovas billions of years ago, however, some stars appeared to be out of the neighborhood. Scientists discovered 42 blue stars that were far too bright and hot for the other stars in the galactic bulge. As you might expect, these are probably blue stragglers. If the existence of such rare stars in this part of the galaxy was suspected, it has now been proven. Until now, this area could not be accurately observed, as younger stars along the line of sight to the bulge made visibility confusing. Of the 42 candidate blue stragglers, scientists believe that 18 to 37 could actually be vampire stars. These stars, although very luminous, are undoubtedly old ladies, between 10 and 11 billion years old. Having vampirized a few companion stars, they have given themselves a much longer lifespan than their fellow stars. As for the rest of the blue stars, they may be genuine young stars or objects outside the bulge. Although scientists believe they have understood how blue stragglers evolve in globular clusters, their observations are not yet complete. Indeed, if one thing is certain, it's that they can never be certain of having fully elucidated the workings of our universe. So vast and constantly evolving is it. Above all, the advent of new, ever more advanced technologies means that discoveries can be made that sometimes drastically call into question past deductions. This is why so many star clusters are constantly in the sights of numerous telescopes. A case in point is the Messier 30 cluster, located in the constellation of Capricorn, some 28,000 light-years from our solar system. Discovered in 1764 by French astronomer Charles Messier, it was initially thought to be a round nebula containing no stars. However, 20 years later, this formation, whose diameter is around 90 light-years, took on the status of a cluster with an indefinable core due to its very high concentration and density of stars. Its spectral study, which classifies it as F3, indicates that it is extremely poor in heavy elements. It is therefore a very old globular cluster in our galaxy, probably 13 billion years old. For astrophysicists, this swarm of several 100,000 stars represents a case study that will certainly enable them to learn even more about the evolution of stars. With the help of the Hubble Space Telescope, astronomers have identified two distinct types of straggler star, just as their colleagues had previously done when studying the 47 Tucanae cluster. In a study published in 2009 by Francisco Ferraro, an astronomer from the University of Bologna in Italy, the hypothesis that blue stragglers can evolve in this way as a result of different processes seems to be confirmed. These stars, which are not as young as they first appear, are indeed the result of stellar encounters. Although their mass is greater than the typical mass of individual stars in Messier 30, they do not all have the same properties, which means that the two formation scenarios already presented are equally valid, but also that they can occur simultaneously in the same cluster. Potential collisions thus lead to the fusion of several stars, which, forced to mix their fuel, fan the flames of nuclear fusion. And as we observed earlier, the evolution of binary systems can just as easily spawn a blue straggler alongside a longtime companion, then devoured on the surface. What's more, by compiling the data collected by the wide-field planetary camera aboard the Hubble Space Telescope, the astronomers found that blue stragglers, although widely scattered within the cluster, are particularly more concentrated near its center than the so-called medium stars that populate it for the most part. They deduced that these blue stragglers are more massive than most of the stars in this structure. Indeed, as Francisco Ferraro explains, more massive stars tend to sink deep into the cluster like a billiard ball sinking into a honeypot. Whatever the process used to bring these stars back to life, they all have one thing in common. Their mass is around twice that of the typical mass of the individual stars in the cluster. To explain this unquestionable concentration in the central region of Messier 30, where interactions between stars are almost inescapable, astrophysicists have developed a hypothesis. They assume that the Messier 30 cluster underwent a major core collapse 1 or 2 billion years ago. During this cataclysmic event, a large number of stars would have been thrown towards the center of the structure, inevitably leading to a rapid increase in their density. As a result, the first family of blue stragglers would have emerged. As a result of these reorganizations, the twin systems would also have been greatly disturbed, inevitably accentuating the vampirism mechanism to which they are highly prone, giving rise to a second line of blue stragglers. In short, the two existing populations of stragglers that populate Messier 30 are the stigmata of the cluster's core collapse, probably 2 billion years ago. For some, this discovery is direct evidence of the impact of star cluster dynamics on stellar evolution. It now remains to be seen whether other globular clusters also possess this diverse population of blue stragglers. The hunt was on for blue stragglers, and consequently for vampire stars. In the years that followed, many researchers set about the task of detecting as many of these stars as possible, also known as cataclysmic variables. In a 2021 publication, Vikrant Jadhav and Annapurni Subramanian report on their meticulous census carried out thanks to the Gaia Telescope. Launched in 2013 by the European Space Agency, the Gaia Telescope offers excellent positional accuracy, making it possible not only to detect blue stragglers in open clusters, but above all, to study them like never before. Studies are now focusing more on open clusters because of the better distinction they offer between stars, as there are fewer of them in the same area, and consequently, they are closer together. The researchers were thus able to study 670 clusters, all over 300 million years old. They were able to identify 868 blue stragglers in 228 distinct clusters. These are mainly found in the most massive and oldest star clusters. They also confirmed that they are mainly located near the center of these same clusters, and all more massive than the extinct stars of the main frequency. Finally, they were able to draw up a detailed inventory of these exotic stars, and even deduce their formation mechanism. According to their study, it turns out that over 54% of blue stragglers are vampire stars that formed by mass transfer, feeding long but surely on their close companion star. 30% of these rejuvenated stars have benefited from a collision with a second star. Finally, 10 to 16% of blue stragglers came into being as a result of interactions between more than two stars. Thanks to this study, we now know a little more about stellar systems. Numerous observations of these blue stragglers are still in progress, notably using ultraviolet imaging integrated into the AstroSat telescope, the first dedicated space observatory, and the Devasthal optical telescope at Nainital, both in India. Nevertheless, globular clusters are not being neglected. Quite the contrary, in fact. One of them, the famous Hercules globular cluster, Messier 13, 25,100 light-years away, is one of the most beautiful objects to observe through a telescope from the northern hemisphere. It too contains numerous blue stragglers. The galactic globular cluster NGC 6256, located in the constellation Scorpius, some 27,400 light-years from our solar system, has also benefited from close observation. In a study published in 2022, scientists reported that it hosts a double sequence of blue straggling stars. Like the Messier 30 cluster, a detailed photometric study of its bulge concluded that it is at a very advanced stage of dynamical evolution, as evidenced by its central segregation of blue stragglers from lighter stars. On the other hand, while Messier 30 reached this stage of evolution around 2 billion years ago, the process in the cluster, located in the Scorpio constellation, seems less ancient. Comparison with collisional models suggests that a short-lived event probably occurred 1 billion years ago, favoring the formation of a population of blue stragglers as a result of collisions. These represent almost 60% of the total population of the observed cluster. However, examination of the positions of the two brightest blue stragglers indicates that the cluster may have undergone an even more recent recollapse, as recently as 1 million years ago. While the vast majority of their fellow stars bear the scars of nearly 12 billion years of existence, these stars give the impression of having recently returned to their adolescence. But this hypothesis will require further study before it proves to be correct. These extremely youthful stars may, after all, be the result of collisions generated by evolving red stars. However, this explanation, though possible, remains weak in the eyes of the specialists. While observing the blue stragglers across various clusters, a group of astronomers led by Professor Ferraro of the Department of Physics and Astronomy at the University of Bologna noticed another peculiarity. They found that some of these puzzling objects form by mass transfer in binary systems, triple systems, and sometimes by stellar collisions, and thus having different structural characteristics, preferred certain environments to others. Their discovery, published in May 2023 in Nature Communications, is conclusive. Young blue stragglers prefer calm environments. The scientists were interested in blue stars with rotational speeds in excess of 40 kilometers per second, or 25 miles per second. Of the clusters studied, all of which are very old, 4 have a low density. These are Messier 4, Omega Centauri, Messier 55, and NGC 3201. The 4 other clusters selected for this observation, which are in contrast very compact high-density clusters, are 47 Tucanae, Messier 30, NGC 6397, and NGC 6752. These groupings of stars, with their different structural characteristics, provide a fantastic laboratory for analyzing the behavior of 320 blue stragglers in 2 contrasting environments. These newly formed stars, either through stellar collision or vampirism, start spinning very fast at the beginning of their rebirth, transforming themselves into veritable cosmic spinning tops. But inevitably, this speed gradually decreases. This is why rotation speed is an essential diagnostic tool for distinguishing newly created blue stragglers from older ones, which inevitably exhibit slower rotation. Following their observations and a survey of the fastest rotating vampire stars, the scientists concluded that fast-rotating blue stragglers are more likely to be found in low-density clusters. In fact, 40% of blue stragglers observed in low-density clusters rotate at high speeds, compared with just 3 to 4% in high-density clusters. So researchers who had previously expected to make the opposite discovery thinking they'd find more fast-spinning blue stragglers in high-density clusters, were extremely surprised by their findings. It opens up a new avenue of exploration for them to try and understand the dynamic processes that characterize the evolution of these vampire stars in different environments. This discovery is likely to have a profound impact on their understanding of the evolution of star clusters, as well as on the consequences of binary systems and stellar collisions. In the course of their observations, scientists are sometimes surprised to discover rare phenomena they may have suspected existed, but had never before had the opportunity to see with their own eyes. For example, they witnessed a super-explosion at the heart of a vampire star system. The super-explosion was detected in 2019, when they carried out yet another search of the countless archives of NASA's Kepler spacecraft. Kepler was designed to find exoplanets by searching for stars that gradually darken as a planet passes through their bright firmament. This technique is therefore ideal for detecting other transient astronomical phenomena, i.e., objects that experience fluctuations in their luminosity. This is how they discovered that Kepler's archives contain some rather unusual data, showing a super-explosion within an unusual binary system. This system consists of a white dwarf star and a brown dwarf, orbiting its companion star every 83 minutes, just 400,000 kilometers apart, roughly the distance between the Earth and the Moon. Because of this close proximity, the white dwarf's intense gravity sucks matter from the brown dwarf. This torn-off material gradually feeds the accretion disk, which spirals toward the heart of the white dwarf. As luck would have it, Kepler was observing in the direction of this system when a very intense phenomenon occurred. He was able to record a super flare coming from this binary system. It brightened by a factor of 1,600 in less than a day, before slowly fading away and then dying out. But that's not all. With Kepler collecting data every 30 minutes, every detail of this massive explosion could be studied. While theories suggest that such an increase in brightness is sudden, the phenomenon in question proved the opposite. In fact, a slow increase in luminosity was observed before the explosion actually took place. Why this slow start? It remains a mystery to this day. According to current theories, this super explosion could take place when the accretion disk reaches a tipping point. As it accumulates matter, it also gradually increases in size. When its outer rim comes into gravitational resonance with the brown dwarf, this would lead to thermal instability. The disk would then overheat, triggering the super explosion. This theory makes perfect sense when we compare the temperature of the accretion disk at the different stages immortalized by Kepler. The accretion disk, whose usual temperature is barely 5,000 degrees Celsius or 9,000 degrees Fahrenheit, would have reached 11,700 degrees Celsius or 21,000 degrees Fahrenheit at the height of the super explosion. It remains to be seen whether Kepler's archives contain any other events of this type, however rare, that would support this hypothesis. As you can see, nature never ceases to surprise us, each time revealing only a tiny part of its mysteries. Among the many other astonishing discoveries, one of them concerns the HR 6819 system. In 2020, a team of astronomers from the European Southern Observatory thought they had discovered the nearest black hole to our Milky Way, accompanied by a star in this system. Shortly after publication, however, colleagues from an international team based at Belgium's Dutch-speaking University of Leuven challenged this original study. According to them, this system does not contain a black hole, but is a two-vampire star system in a transitional stage, extremely rare to observe, although not marginal on the scale of the universe. To unravel this mystery, the two teams agreed to join forces. After agreeing that there were indeed two sources of light in this system, they turned their attention to how far apart they were. Are they two stars orbiting each other in a confined space, or two stars relatively far apart? Thanks to data collected by the Gravity and Multi-Unit Spectroscopic Explorer instruments on the European Southern Observatory's Very Large Telescope Interferometer, they were able to confirm that these two light sources are very close together, only a third of the distance separating the Earth from the Sun. What's more, they believe they witnessed the immediate consequences of a vampire star attack. Indeed, as one of the two stars was stripped by its companion, the latter began to spin much faster than before. The astronomers, lucky enough to have been able to capture this brief post-interaction phase, intend to take a closer look at this vampirism in action. Perhaps they will finally be able to understand how this phenomenon affects the evolution of massive stars, and de facto, the formation of their associated events, such as gravitational waves and violent supernova explosions. And as a result, another mystery remains to be solved. Where does the black hole closest to our Earth hide? To date, astronomers have counted over 1,000 cataclysmic variables. The two stars in this type of system are inevitably close to each other, so that the white dwarf is able to suck matter out of its donor star. But only a dozen of these duos have orbital periods of less than 75 minutes. In 2022, Kevin Burge of MIT's physics department published in the journal Nature that he had spotted one of these cataclysmic variables 3,000 light-years away, in the direction of the constellation Hercules. The two stars in question are so close together that the orbit, which takes just 51 minutes to cover, is the shortest ever observed for a cataclysmic variable. This duo, named ZTFJ 1813 plus 4251, is therefore after a very long life of nearly 8 billion years in full transition. The white dwarf, whose diameter is around 1.5 times that of the Earth, and whose mass is approximately 56% more massive than the Sun, looks rather strange compared to its companion, which is a star similar to our Sun on the verge of becoming a red giant. Above all, scientists have discovered that the vampire star has finished absorbing its neighbor's hydrogen and is beginning to strip it of its helium. This infernal duo is therefore in the process of switching from hydrogen accretion to helium accretion. While they were aware of the existence of cataclysmic hydrogen and cataclysmic helium variable populations, the process by which these stars switch from one to the other was not yet known. Their simulations predict that in approximately 70 million years, the two stars will be so close that their orbital period will be reduced to 18 minutes. The duo will then become a cataclysmic helium variable. They have thus clearly identified the missing link in astrophysics that could explain this transition. When the two stars are close to each other, the inevitable will happen. They will merge and explode. putting an end to the emission of gravitational waves. After this nova, will calm return to this part of the cosmos? And if so, for how long? Unless a black hole appears. During this sudden event, in which both stars are subjected to incredible convulsions, the outer parts of the hydrogen layer and many fragments of the molten products are literally ejected into interstellar space. Depending on the mass and composition of the two stars forming this pair, their evolution may differ. Cataclysmic variables are classified into several distinct groups, often named after the archetype of a bright star with the same characteristics. These include Geminorum variable stars, magnetic or polar cataclysmic variable stars, intermediate polar variable stars, AM Canem, Venaticorum variable stars, and SW Sextantis variable stars. The former, also known as dwarf novae, undergo large explosions caused by deformations of the accretion disk when their rotation enters resonance with the orbital period of the companion star. As for magnetic systems, most of them feature strong variable polarization. Intermediate polars show a partially destroyed accretion disk, while polars prevent the formation of an accretion disk. For the moment, however, the most spectacular phenomenon ever studied is that which causes the vampire star to self-destruct during a supernova. When the accretion process lasts long enough, it leads the white dwarf, the vampire star, to reach the Chandrasekhar limit. The Chandrasekhar mass corresponds to the maximum electron degeneracy pressure an object can withstand, without undergoing gravitational collapse. To the extent that the white dwarf exceeds this limit, the increasing internal density causes the carbon to melt abruptly. This leads to a Type 1a or thermonuclear supernova explosion, which is fatal. The vampire star, having been too greedy, undergoes a cataclysmic explosion, leading to its disintegration. After shining like no other of its many neighbors, it disappears forever from the cosmos, leaving only the remnants of its explosive end of life. Our interstellar journey is coming to an end. As you've already seen, vampire stars are fascinating asteroids that reveal many secrets about stellar evolution. By observing these binary systems, where a white dwarf relentlessly sucks matter from its more massive companion, called the donor, astronomers can study the different phases in the life and death of these strange stars. These stars, whose activity consists of sucking up matter from their nearest neighbors, are also the source of spectacular phenomena, such as novae, supernovae, and even gamma-ray bursts, which enrich the universe with chemical elements. Thanks to space telescopes and ground-based instruments, scientists have detected numerous vampire stars, mainly at the heart of the oldest stellar clusters encircling our galaxy. These stars, with their unlimited appetite, demonstrate just how dynamic and relatively complex the cosmos is, where matter circulates between stars in a variety of sometimes extraordinarily surprising interactions.